Saturn, the jewel of the solar system, is home to a moon unlike any other. This moon holds its own unique secrets and is none other than Titan. Shrouded in a thick, hazy atmosphere, it hides a surface that changes how we think about what a moon can be. Beneath its orange veil lies a landscape riddled not with water, but with liquid methane and ethane. Titan is the only place in our solar system where there is stable liquid on the surface. But these seas and lakes are composed not of water, but of hydrocarbons, substances that would be exotic and deadly on Earth. Imagine standing on the shore of Kraken Mare, Titan's largest sea, covering more than 193,000 square miles, an area larger than the state of California. The surface of this vast body of liquid methane is gently rippling, eerily calm, and under a sky perpetually shrouded in an orange haze. The Cassini and Huygens missions have discovered these amazing features, revealing lakes and seas whose coastlines change with the seasons, and even possible signs of cryovolcanism, volcanoes spewing icy substances instead of molten rock. Methane and ethane condense and fall from the sky, cutting channels and filling pools to evaporate and start the cycle. But how is this cycle maintained on Titan? The methane in the atmosphere should be broken down by sunlight, but it continues to exist. Could there be an underground ocean, a reservoir that replenishes Titan's surface with fresh methane? Join us as we travel the seas of this moon. Delve into the discoveries made by the Cassini and Huygens missions and explore its mysteries. Before the Cassini mission, our knowledge of Titan was limited by its size and dense nitrogen atmosphere. Cassini changed all that, revealing Titan as a dynamic world with complex geologic and atmospheric processes. The mission made groundbreaking discoveries about Titan. One of the most striking was the confirmation of the existence of lakes and seas made of liquid methane and ethane. These hydrocarbon bodies are replenished by rainfall from the dense, nitrogen-rich atmosphere, creating a methane cycle similar to the Earth's water cycle. This cycle is not the only Earth-like feature. On Titan's surface, near the equator, are vast dune fields that resemble deserts on Earth. However, instead of silicate sand, these dunes are composed of solid water ice covered with organic compounds that precipitate out of the atmosphere. When the Huygens probe descended to the moon's surface, it took detailed measurements and images, providing the first direct view of this alien world. The probe's data showed that the landscape was formed by both liquid and solid hydrocarbons. Perhaps most intriguing is the evidence of a subsurface ocean beneath Titan's icy crust. Gravity measurements by Cassini have shown that this hidden ocean may consist of water mixed with ammonia, which adds Titan to the list of celestial bodies on which life may exist, but more on that later. Long-term observations have also documented seasonal changes on Titan. Each season lasts about 7.5 Earth years, and Cassini has recorded the transition from fall to winter at Titan's south pole and the onset of summer in the north. These seasonal changes affect methane lakes and seas, providing additional insight into Titan's dynamic climate. But as exotic as Titan sounds, in some respects it's one of the most hospitable worlds in the solar system. The moon's nitrogen atmosphere is so dense that a person wouldn't need a spacesuit to walk on the surface, just an oxygen mask and protection from the cold. The temperature on the surface is about minus 290 degrees Fahrenheit. The dense atmosphere also means that raindrops fall much more slowly than they do on Earth, while Earth's rain falls at about 20 miles an hour. Scientists have calculated that rain on Titan falls at about 3.5 miles per hour, or about 6 times slower than Earth's rain. However, let us return to the hydrocarbon seas and lakes. The three largest seas, Kraken Mare, Leia Mare, and Punga Mare, are located near Titan's North Pole and consist mainly of liquid methane and ethane. Recent analysis of data from Cassini's bistatic radar experiments has provided new insights into these seas. Unlike monostatic radar, which only sends and receives signals from the spacecraft, bistatic radar reflects the signal from the surface and records its reflection on Earth. This method allows scientists to gather more detailed information about the composition and properties of the surface. A research team led by Cornell University used bistatic radar data from several Cassini flybys to assess the composition and roughness of the Moon's sea surface. The results revealed significant differences in the surface layers of these seas, depending on their latitude and proximity to rivers and estuaries. For example, the southernmost, Kraken Mare, had the highest dielectric constant, indicating differences in water body composition. Interestingly, despite the complexity of these seas, surface conditions during the overflights were mostly calm. Radar data showed that waves in Kraken Mare, Leia Mare, and Punga Mare did not exceed 1/10 of an inch, with slightly rougher conditions near the coastal areas and estuaries, where waves reached 1/5 of an inch. These variations indicate the presence of tidal currents similar to those on Earth. Another interesting discovery was the difference in water composition between the rivers and the open seas. The rivers feeding Titan's seas are composed mostly of pure methane, while the seas themselves are richer in ethane. This echoes the behavior of freshwater rivers mixing with salty oceans on Earth, highlighting the dynamic and Earth-like nature of the hydrocarbon cycle. The methane cycle on Titan works much like the water cycle on Earth. Methane clouds form in the dense nitrogen atmosphere, causing methane rain that fills rivers and seas. The rain consists mostly of pure methane, but trace amounts of ethane and other hydrocarbons are present, which affect the composition of the seas. The calmness of Titan's seas, combined with their unique composition, provides a wealth of information about meteorological and geological processes on the Moon. Continued analysis of Cassini data provides more and more information about the climate and the possibility of life on the Moon. However, the methane found in the Moon's dense atmosphere is constantly being destroyed by sunlight. The persistence of the gas has long puzzled scientists, leading to many theories. One of the leading hypotheses is the existence of a subsurface ocean beneath Titan's methane-rich icy crust. This ocean, consisting of water mixed with ammonia, may be a significant source of matter. Recent research has provided insight into Titan's internal structure. By analyzing gravity field measurements from Cassini, scientists have concluded that the thickness of Titan's ice shell varies, which may indicate an active internal environment with constant convection currents. These currents may help move subsurface water and ammonia, creating pockets of liquid that can erupt through the ice in the form of cryovolcanoes. Cryovolcanoes, or ice volcanoes, can erupt and release methane into the atmosphere, replenishing gas reserves. Research shows that over its 4.5 billion year history, the Moon has experienced several significant outgassing events. The most recent event is thought to have occurred about 500 million years ago and was caused by convection in the icy crust. Earlier events were caused by similar processes in its core and crust, suggesting a dynamic geologic history for the Moon. Cassini's gravity field measurements played an important role in these discoveries. By analyzing slight changes in the spacecraft's radio signals as it orbits Titan, scientists can infer the presence of a subsurface ocean. These measurements show that the Moon's shape changes over time, and noticeably more than if it were a solid body. If methane is indeed being replenished from the subsurface ocean, it means that Titan has a very active and complex interior. This ongoing geologic activity may also affect Titan's potential habitability, making it a prime target for future exploration. Titan's geologic activity is a fascinating field of study, revealing a dynamic and enigmatic Moon. The strength of its rocky core plays a crucial role in geologic dynamics. Studies show that the core rock is quite strong, making it resistant to the types of fractures and faults that define tectonic activity on Earth. However, the tremendous pressure from the overlying ice and fluid layers can still lead to significant geologic activity, albeit of a different nature. The interaction between rocks and the subsurface ocean is a key area of research. On Earth, hydrothermal vents on the ocean floor create an environment where water and rocks interact to support viable ecosystems. If similar interactions occur on Titan, this could affect the Moon's habitability and the possibility of life. The presence of organic compounds in the atmosphere detected by Cassini suggests that complex chemical processes are taking place there. Titan has long attracted the attention of scientists for its terrestrial characteristics and the possibility of extraterrestrial life. Its thick atmosphere, liquid seas, and subsurface ocean all present intriguing possibilities for life. One of the most attractive aspects of Titan is its complex organic chemistry. The Cassini-Huygens mission showed that its atmosphere is very rich in organic molecules, and a dynamic cycle that replicates Earth's water cycle provides the raw materials necessary for life to form. This year's research focused on the possibility of organic molecules entering this subsurface ocean. Impact events from comets and meteorites could be a mechanism for delivering organics through the icy crust. The impacts generate heat, the ice melts, and the organic compounds mix with the ocean below. Over billions of years, this process could have created a rich environment that supports life. However, the idea that life exists on Titan faces certain difficulties. The extreme cold and lack of sunlight make it unlikely that life as we know it exists on the surface. In addition, recent research suggests that the rock beneath Titan's ice is too strong to be geologically active, which may limit the water-mineral interactions critical to life. Despite these challenges, Titan remains one of the most promising places in our solar system to look for life. The complex interplay of organic chemistry, liquid methane seas, and subsurface oceans offers many opportunities for life to evolve, even if it's unlike anything we've seen before. NASA's Dragonfly mission will continue to explore this moon's potential for life in the coming years. The innovative drone, scheduled for launch in 2028, will study Titan's surface and atmosphere in unprecedented detail, providing crucial data that can confirm or deny the presence of life. The mission aims to analyze the composition of organic matter, study weather patterns, and look for signs of prebiotic chemistry. Central to this mission is the Dragonfly Mass Spectrometer, or DRAMS for short, an advanced instrument designed to analyze the chemical composition of lunar surface materials. DRAMS is critical to studying prebiotic chemistry on Titan. This mass spectrometer will analyze samples of surface material to detect organic molecules that are the building blocks of life. By studying these molecules, scientists hope to discover chemical processes that could lead to the emergence of life like those that occurred on the early Earth. The instrument works by ionizing the sample material, by bombarding it with energy to charge atoms. These ionized atoms then pass through sensors that detect their mass-to-charge ratio, creating a detailed chemical fingerprint of the sample. This process allows DRAMS to identify a wide range of organic compounds and their distribution in different surface environments. To collect samples, Dragonfly is equipped with a drill for acquisition of complex organics. This drill will extract small samples from the lunar surface, which will then be analyzed by the DRAMS instrument. The instrument is then placed in the attic of the vehicle, where the samples are vaporized in an oven or irradiated with a laser to prepare them for analysis. Dragonfly's ability to fly between different parts of the lunar surface is a significant advantage. This mobility allows it to explore different geologic environments, from methane lakes to organic-rich dunes. At each location, unique samples will be taken for analysis using DRAMS. In addition to DRAMS, Dragonfly will carry other scientific instruments, to measure atmospheric conditions, weather patterns, and surface properties. This comprehensive suite of instruments will provide a holistic view of Titan's environment, further expanding our understanding of Titan's habitability. The search for life on Titan is not just about finding microbes or complex organisms. It is about understanding the fundamental processes that can lead to the origin of life and help us understand the conditions necessary for life to emerge in the universe. We look forward to the upcoming Dragonfly mission and the new discoveries that will shed light on the habitability potential of not only Titan, but other icy moons and exoplanets throughout the universe. Stay tuned as we continue to explore the mysteries of space and bring you the latest discoveries in our quest to understand the universe. Imagine a universe that's just beginning, only a few 100 million years old, a time when the first galaxies were forming. Thanks to the James Webb Space Telescope, we've made groundbreaking discoveries that take us back to an ancient era. Before you is a universe where every tiny point of light is a galaxy, a vast cluster of stars, planets, and mysteries. Among these countless galaxies, some are so distant that their light took billions of years to reach us. Studying these distant galaxies is of great importance because it helps us understand the early stages of cosmic evolution and the formation of structures in the universe. This spring, astronomers using JWST were able to peer into the earliest universe, discovering galaxies that existed more than 13 billion years ago. One of these discoveries concerns galaxies with red shifts between 9 and 11. But what does that mean? Simply put, redshift is a measure of how much light from these galaxies has been stretched by the expansion of the universe. The greater the redshift, the farther back in time we're looking. The light from these newly discovered galaxies began its journey when the universe was less than 1 billion years old. At that time, our Milky Way was just beginning to form, and only the first stars were illuminating the cosmos. Not only are these galaxies incredibly distant, but they're also incredibly young, giving us a glimpse into the formative ages of the universe. So, how did galaxies like ours originate and evolve over billions of years? Let's find out. In the depths of space, hidden among countless stars, lies Sears 43833. This galaxy, located at redshift 8.76, takes us back to a time when the universe was less than 600 million years old. Its light, traveling through the vastness of space, brings us valuable information about the early stages of galaxy formation. Looking deeper, astronomers have approached Sears 16943, an even more distant galaxy with a redshift of 11.4. This galaxy is one of the oldest ever observed, emitting its light at a time when the universe was only 400 million years old. Studying such distant galaxies helps us understand the processes that led to the formation of the first stars. Finally, MAX 0647-JD appears before us, observed at redshift 10.17. This galaxy's light has taken more than 13 billion years to reach us. Its discovery was made possible by the powerful capabilities of JWST, revealing its complex structure and providing insight into the early universe. But what is redshift, and why is it so important? Imagine a car traveling away from you, just as the car's taillights appear increasingly red as they move away from us. The light from distant galaxies is stretched and shifted toward the red spectrum. The higher the redshift, the more distant and ancient the galaxy is. Redshift is an essential tool for astronomers. It allows us to measure the distance to these galaxies and therefore their age. Light from these galaxies began its journey billions of years ago, creating a snapshot of the early stages of the universe. By studying galaxies at different redshifts, we can piece together the story of cosmic evolution. Open galaxies are not just distant objects. They are time capsules that provide a glimpse into the early universe. These discoveries address fundamental questions about our existence. How did the first galaxies form? What processes drove their evolution? And what does this tell us about our home, Milky Way? The discovery of these distant galaxies was made possible by two significant observing programs. These programs used the advanced capabilities of the James Webb Space Telescope to look deeper into the universe than ever before. The first program used the director's discretionary time to focus on observing high redshift galaxies. Under the leadership of principal investigator Pablo Arrabal-Arro. This program aimed to study the early universe, searching for galaxies formed just a few 100 million years after the Big Bang. By targeting specific regions of the sky, DD2750 successfully identified several ancient galaxies, including Sears 43833. The second program was part of an overall observational program led by principal investigator Dan Coe. This program was aimed at detailed spectroscopic studies of known candidates for high redshift galaxies. The GO 1433 program was instrumental in confirming the redshifts of these galaxies and studying their properties in detail. As part of this program, the team observed two other objects, obtaining valuable data on their composition and structure. JWST used two of its most powerful instruments, NIRSpec and NIRCam, to make these groundbreaking observations. Let's take a closer look at how these instruments work. NIRSpec, or near-infrared spectrograph, is designed to simultaneously obtain spectra of multiple galaxies. This instrument can analyze light from galaxies to determine their chemical composition, temperature, density, and redshift. This instrument is crucial for studying the detailed properties of galaxies and understanding their evolution over time. NIRSpec operates in the near-infrared, which is ideal for observing distant galaxies. By dividing the incoming light into its constituent wavelengths, the instrument creates a detailed fingerprint of each galaxy, revealing its unique characteristics. NIRCam, or near-infrared camera, serves a different but complementary purpose. It takes high-resolution images of galaxies, allowing astronomers to study their morphology and structure. The camera is particularly effective at observing faint and distant objects, making it indispensable for identifying and analyzing high redshift galaxies. The NIRCam's wide field of view allows large areas of the sky to be captured in a single image. This capability is critical for surveys such as DD2750 and GO 1433, where astronomers need to observe many galaxies simultaneously. By combining detailed spectra with high-resolution images, scientists can build a complete picture of these ancient galaxies. So what exactly did the scientists see? These ancient galaxies are incredibly small compared to our Milky Way. They are less than a kiloparsec across. By comparison, that's about 1,000 times smaller than our Milky Way. Despite their diminutive size, they're bustling with activity typical of the young star-forming galaxies of the early universe. Some of them even exhibit complex structures affected by gravitational lensing, a phenomenon in which a massive foreground object distorts the light from a background object, allowing us to see them in greater detail than would otherwise be possible. But why do these size differences matter? It's the small size of these galaxies that suggests they're in the early stages of their evolution. In the young universe, galaxies were still forming and merging, leading to intense periods of star formation. These compact galaxies are like snapshots of the early universe, showing us how galaxies start their lives and grow over time. What do these galaxies look like? Sears 43833, for example, looks like a bright, compact object with hints of structure, indicating regions of intense star formation. Sears 16943, although smaller, also shows signs of active star formation. In contrast, MAX 0647-JD shows a more complex morphology due to lensing effects and shows multiple images of the same galaxy. However, it's the understanding the light of these galaxies that's key to unlocking their secrets. This is where spectral energy distribution, or SED, comes into play. The SED represents the range of energy emitted by a galaxy in different wavelength ranges, from ultraviolet to infrared. By studying the SED, astronomers can infer various physical properties of a galaxy, such as its age, mass, and star formation rate. We use the NIRSpec and NIRCam data on JWST to create the SED. After that, we can model it using software that simulates different galaxy formation and evolution scenarios. By fitting the observed data to these models, we can estimate the galaxy's stellar mass, star formation history, and other important parameters. The SEDs of these galaxies indicate a relatively young stellar population, with intense star formation occurring less than 100 million years ago. A detailed analysis of these SEDs helps us piece together the life history of these ancient galaxies. As we've already mentioned, the light from these distant galaxies contains a wealth of information, especially in the form of emission lines. Emission lines are bright lines appearing at specific wavelengths in the spectrum that occur when elements in the galactic gas become energized and emit light. Each element produces a unique set of lines, much like a fingerprint, which allows us to determine the chemical composition of the galaxy. In addition to identifying elements, emission lines also reveal the physical properties of the galaxy's gas and stars. By analyzing the intensity and ratio of these lines, astronomers can estimate the rate of star formation, showing how many new stars are being born in the galaxy. For example, a strong H-alpha emission line indicates a high star formation rate, indicating that the galaxy is actively producing new stars. The emission lines also help determine the oxygen content of the galaxy, which is an indirect indicator of its overall metallicity. This tells us how many generations of stars have existed, enriching the galaxy with heavier elements over time. Understanding these properties helps to compile the history of the galaxy and determine the stage of its evolution. One of the most intriguing features observed in these distant galaxies is damped Lyman alpha, or DLA. But what exactly is a DLA? Simply put, the DLA is a broad absorption line in the spectrum of a galaxy caused by the presence of large amounts of neutral hydrogen gas. This absorption line is much broader than normal lines, indicating a significant amount of gas. DLAs are important because they allow us to directly measure the amount of neutral hydrogen in the early universe. This information helps us understand how galaxies acquire the gas that fuels star formation and how they evolve. By studying the DLA, we can learn about the conditions in the universe when these galaxies formed. The detection of DLA in these galaxies involves analyzing their spectra for characteristic broad absorption features. This process allows us to quantify the amount of gas present and understand the environment around young galaxies. The presence of DLA in these galaxies tells us that they're rich in neutral hydrogen, which is crucial for star formation. It also provides insight into the intergalactic medium, the space between galaxies, and its role in galaxy formation. By comparing DLA features to different galaxies, we can build a more complete picture of the early universe. The discovery of these ancient galaxies provides a unique opportunity to compare them to other known superluminous galaxies. Unlike their more evolved counterparts, these newly discovered galaxies have distinctive characteristics that set them apart from others. What makes these new discoveries special is the unusual amount of dense gas surrounding them. This gas, consisting mainly of hydrogen and helium, is one of the earliest elements to exist in the universe. The presence of such dense gas is unusual because it indicates that these galaxies are in the earliest stages of their evolution. This dense gas is likely to fuel the formation of new stars, playing a crucial role in their evolution. Another unique feature of these galaxies is their low metallicity. In astronomy, metallicity refers to the content of elements heavier than hydrogen and helium in a galaxy. Low metallicity also confirms that these galaxies have not gone through many star formation cycles, which means that they have fewer heavy elements and that they're in the earliest stages of their evolution. Thus, they're an ideal laboratory to study the initial stages of galaxy formation and their evolution. This information will help us piece together the sequence of events that led to the formation of galaxies in the early universe. These discoveries also fit into the broader context of understanding the history of the universe. During the period known as the Age of Reionization, the universe went from opaque to transparent. The galaxies discovered by JWST are among the first to contribute to the reionization process by ionizing the gas around them. The next steps will involve creating large statistical samples of galaxies to estimate in detail the prevalence and brightness of their features. Researchers will continue to study where the gas is, how much of it is near the center of galaxies, and whether it's primordial or already contains heavier elements. In the meantime, we'll await new results and discoveries, which we will be sure to report to you. Is the fabric of our universe woven with the threads of time travel, or is it a tapestry of unattainable dreams? Our documentary series embarks on a quest through the corridors of science and imagination, probing the boundaries of what we understand about the cosmos and our place within it. Can we bend time to our will, traversing the past and future as easily as we journey from one destination to another? We explore the tantalizing concept of time travel, delving into the realms of physics and fantasy to uncover whether our universe harbors the potential for such extraordinary journeys. What barriers stand between us and the realization of a warp drive, a technology that could tear through the cosmic speed limit set by Einstein's theory of relativity? We investigate the scientific hurdles and breakthroughs that tease the possibility of faster-than-light travel, asking what's stopping us from building a warp drive. In the cosmic ballet, where stars are born and black holes devour, the concept of white holes presents an intriguing counterpoint, an impossible possibility that challenges our understanding of astrophysical phenomena. Could these theoretical reverse black holes exist, ejecting matter and light into the universe, and what would their discovery mean for our understanding of cosmic evolution? Finally, we turn to a groundbreaking discovery, a new law of nature that bridges the gap between physics and biology, offering a framework to predict the course of evolution itself. How does this new law of nature redefine our understanding of life's complexity and its interplay with the physical universe? Join us as we navigate these profound questions, seeking answers at the intersection of known science and speculative theory. This series is an invitation to journey beyond the horizon of current understanding to ponder the mysteries that lie at the heart of existence. Welcome to a documentary experience where the impossible becomes a gateway to new realms of knowledge. Imagine a canvas of moments woven with the threads of time. Matter that stretches endlessly in all directions, capturing every choice, every event, every heartbeat. What if you could navigate this intricate fabric? What if you could go back in time, look into the future, or even change the course of history? Time, it governs our lives, but it remains one of the most mysterious phenomena in the universe. We measure it, We chase it, but can we control it? The concept of time travel has intrigued humanity for generations, inspiring countless works of fiction and sparking rigorous debate. But what can science say? Can time travel ever move from the pages of science fiction to the annals of scientific fact? Einstein's theory of relativity opened the door to this possibility by suggesting that time is not a constant, but a variable that can be manipulated. In addition, there are black holes, cosmic phenomena so powerful that they can distort not only light, but time itself. Did you know that astronauts aboard the International Space Station age slower than humans on Earth, even if only by a fraction of a second? This is not science fiction. It is a proven consequence of traveling at high speeds. So let us journey through the corridors of time. We'll explore the science, paradoxes, and limitless possibilities that may one day make time travel a reality. Welcome to a journey through time. Long before the advent of science as we know it, humankind was fascinated by the heavens and the passage of time. Ancient civilizations paid attention to the stars, sun, and moon, creating elaborate calendars and methods of measuring time. Transported to the modern era, this fascination has found a new canvas: film and literature. The concept of time travel has been a recurring theme, offering both escapism and a platform for intellectual curiosity. In 1895, H.G. Wells wrote the novel The Time Machine, which, by the way, not only popularized the term time machine, but also introduced the idea that time could be navigated like the dimensions of space. Then came Back to the Future, a pop culture powerhouse that took the concept of time travel and made it accessible to a whole new generation. Who could forget the DeLorean, the magnetic condenser, the flux capacitor, and Doc Brown's charming eccentricity? But it's not just a Western phenomenon. The allure of time travel knows no cultural or linguistic boundaries. From the Japanese Steins Gate to the Soviet Ivan Vasilievich changes profession, the theme of time travel resonates around the world. So what is it that attracts storytellers to this concept? The allure of rewriting history? The excitement of the unknown? Or perhaps the philosophical questions such journeys raise? It's a desire fueled by a mixture of nostalgia and anticipation, a longing to revisit cherished memories or leap into the promises of tomorrow. And as we stand on the cusp of scientific discoveries that could turn dreams into reality, the question becomes more important than ever. Could we? Should we? And what if we did travel through time? The blackboard is the canvas on which the abstract becomes possible. Here, equations like E equals mc squared are not just symbols. They're keys to understanding the universe. But can they unlock the secrets of time travel? From silver screens to living room TVs, time travel has been portrayed in countless ways. But let's peel back the layers of fiction and delve into the science that can make time travel more than just a plot device. Meet space-time, the four-dimensional fabric of our universe. According to Einstein's theory of relativity, this fabric can be bent and deformed by mass and energy. But can it be torn or twisted to create a path through time? Time dilation, a consequence of Einstein's theory, suggests that time can flow at different rates depending on the speed of motion or the gravitational field. For example, astronauts on the International Space Station age slightly slower than people on Earth. Experiments with particle gas pedals and atomic clocks have provided empirical evidence of time dilation. It's been observed that particles traveling near the speed of light decay more slowly than their stationary counterparts. In addition, there are wormholes, hypothetical tunnels in space-time that could theoretically allow time and space to be shortened. Although somewhat speculative, the math suggests that they are possible. Leading physicists and cosmologists have voiced their opinions on the matter, offering theories that range from plausible to downright bizarre. Some even suggest that quantum mechanics, the science of the very small, may play a role in making time travel possible. And let's not forget black holes, the mysterious titans of space. Their enormous gravity is so strong that it distorts not only space but time itself. Could these cosmic phenomena be a gateway to other times? The scientific community is far from consensus. Time travel raises questions that challenge the very foundations of physics, from the nature of reality to the concept of causality. They say time goes forward, always forward, and never backward. But what if we could leap forward, skipping years, decades, or even centuries? The idea might not be as far-fetched as it seems. When it comes to slowing down time, speed becomes the main parameter. According to Einstein's theory of relativity, the faster you move in space, the slower you move in time. So, could extreme speed be our ticket to the future? Believe it or not, time travel to the future has already been done, albeit on a minuscule scale. Astronauts aboard the International Space Station experience time dilation and age a little slower than their counterparts on Earth. Let's turn our attention to the twin paradox, the famous thought experiment that takes time dilation to a new level. Imagine twins separated at birth. One travels through space at near light speed, while the other remains on Earth. Upon reunion, the space twin will appear younger. Achieving speeds close to the speed of light would greatly enhance this effect. However, such speeds are currently beyond the reach of our technology. Not to mention the energy requirements would be astronomical. Scientists and engineers are wrestling with these problems, researching propulsion technologies that could, one day, make near-light-speed travel possible. But even then, can the human body withstand such a journey? Imagine a future where time dilation capsules are as common as airplanes, allowing people to jump into the future to glimpse advanced civilizations or even avoid catastrophes. Will knowledge of the future be a gift or a curse? And what will it mean for the concept of free will? From science fiction to science articles, wormholes have captured our collective imagination. These hypothetical tunnels in the fabric of space-time may turn out to be the cosmic shortcuts we've been dreaming of. But what are wormholes, and could they be the key to time travel? Imagine folding a piece of paper so that 2 points touch, and then poking it with a pencil. In space-time, the wormhole would be that pencil, creating a straight path between 2 distant points. This concept gained traction in the scientific community thanks in part to Carl Sagan. While writing his novel Contact, he consulted with physicist Kip Thorne to explore the scientific possibility of using a wormhole for interstellar travel. Today, physicists are delving deeper into the math of wormholes. While the general theory of relativity allows for their existence, the equations also assume that they collapse too quickly for anything to pass through them. Theoretically, by introducing some exotic matter, for example, it could counteract the gravitational forces causing the wormhole to collapse, keeping it open long enough for something or someone to pass through. The portrayal of wormholes in popular media often glosses over these complexities. They're usually portrayed as stable, luminous vortices. But the reality, if they exist, can be much more volatile and unpredictable. Despite the lack of empirical data, the study of wormholes is a dynamic area of research. Scientists use computer modeling and indirect observations to understand their properties and potential uses. Imagine the possibilities if wormholes could be used for time travel. One end could be anchored in the present, the other in the future, or the past. The implications for research and even for preventing global catastrophes are staggering. Wormholes open the door to questions not only about where we might go, but when. And as we approach the potential discovery of these cosmic shortcuts, we must ask ourselves, are we ready for the responsibility associated with such power? In the world of the very small, where particles are also waves, and reality itself seems blurred, lies the quantum world. Could this region of uncertainty hold the keys to unlocking time travel? Quantum mechanics challenges our everyday understanding of the world. Take the two-slit experiment, in which particles behave as both particles and waves. This duality suggests that, at the quantum level, the fabric of reality is much more malleable than we thought. Great minds like Richard Feynman and Niels Bohr have delved into the mysterious world of quantum mechanics, a theory that's been incredibly successful in explaining the behavior of matter and energy at extremely small scales. Some physicists suggest that quantum mechanics may offer a basis for time travel. Quantum tunneling, for example, allows particles to pass through barriers as if they're ghosting through walls in the two-slit example. Can a similar principle enable time tunneling? Quantum computing is a new field that uses the principles of quantum mechanics to perform calculations at speeds unimaginable to classical computers. Some speculate that quantum algorithms could solve equations related to time travel that are currently too complex for today's computing machines. The concept of quantum entanglement adds interest. Imagine two particles cooked together in a certain way. Once entangled, these particles become interconnected, forming a single quantum system. The truly stunning aspect of entanglement is that the state of one particle instantly affects its entangled partner, regardless of the distance separating them. This could be across the room or even across the galaxy. Change the spin of one, and the other instantly changes. Albert Einstein famously called it spooky action at a distance. At first, he didn't like this idea because it seemed to violate the limit of the speed of light set by his theory of relativity. Since then, however, numerous experiments have confirmed that entanglement is a real and fundamental aspect of quantum mechanics. Could such an effect at a distance make a difference to instantaneous time travel? While the intersection of quantum mechanics and time travel is still in the realm of speculation, it is a hotbed of scientific research. Researchers are studying everything from quantum loops in time to the role of quantum gravity in the early universe. Imagine a future in which the principles of quantum superposition could account for multiple timelines or realities. What if you could exist in a superposition of past and present? Could quantum mechanics be the final piece of the puzzle in our quest to conquer time? Moving on, let's move from the world of the microscopic scale to the grandiosely large one, black holes, mysterious titans of space whose gravity is so strong that not even light can leave them. But could these celestial phenomena hold the secret to time travel? Enter the concept of closed time-like curves. A closed time-like curve, or CTC, is a path in spacetime that loops back on itself. Theoretically, an object or even a person traveling along a CTC could end up in an earlier point in time. The idea was first proposed by physicist Kurt Gödel in 1949. Gödel's solution to Einstein's field equations suggested that rotating universes could contain paths looped in time. However, these solutions required certain conditions, such as a universe filled with rotating matter. Although Gödel's model is considered physically implausible in most cases, it has opened the door for other scientists to explore the concept. The main challenge is to find a scenario in which STSSs could exist without violating the laws of physics. One such scenario involves rotating black holes, known as Kerr black holes. Massive gravitational and rotational forces can theoretically twist space-time into loops, creating CTCs. But there's a catch. Most models predict that the center of a rotating black hole, known as a singularity, will be ring-shaped rather than point-shaped. This ring feature could potentially serve as a gateway to the CTC. However, powerful gravitational forces could also create a barrier, known as the Cauchy horizon, beyond which the laws of physics are violated. The study of CTCs and black holes is fraught with paradoxes and uncertainties. For example, if CTCs exist, they can lead to paradoxes in which cause and effect are reversed. This has prompted some physicists to propose the chronology defense hypothesis, which suggests that the laws of physics prevent such paradoxes. Imagine the possibilities and dangers of approaching a rotating black hole. Would we ever be able to navigate safely through such a treacherous region of space-time? And if we could, what would we find on the other side? Another universe? Another time? In addition to black holes and closed time-like curves, there's another cosmic mystery that could potentially open a path through time: cosmic strings. These hypothetical one-dimensional cracks in the universe may be remnants of the Big Bang itself. Cosmic strings are thought to have formed in the early moments of the universe as they cooled down after the hot and dense state of the Big Bang. These strings would have been thinner than an atom, but incredibly dense, and would have had a tremendous gravitational pull. Although still theoretical, cosmic strings offer intriguing possibilities for time travel. Physicists J. Richard Gott and William Hiscock have made significant contributions to our understanding of these mysterious objects. Gott suggested that a cosmic string traveling at the speed of light could theoretically distort spacetime enough to create a loop allowing time travel into the past or future. However, the existence of cosmic strings is still a matter of debate. Their detection would require astronomical observations on scales that are currently beyond our capabilities. Moreover, if they do exist, harnessing their power for time travel would be a challenge. Now, let us return to quantum entanglement. We've already explored how entangled particles are connected in ways that transcend ordinary spatial distances. Can they be bound in time? Some theories suggest that entangled particles can be used to transmit information not only in space, but also in time. Imagine a future in which quantum entanglement is used to create a kind of quantum internet that allows instant communication across eras. The intersection of cosmic strings and quantum entanglement is a frontier of theoretical physics rife with unanswered questions and untapped potential. Researchers are exploring how the two phenomena might be connected and what this might mean for our understanding of time travel. Imagine a scenario in which cosmic strings are manipulated at the quantum level through entanglement. This would represent a merger of the very large and the very small, a meeting point of cosmic and quantum scales that could revolutionize our concept of time travel. As we venture into the realm of time travel, we face many paradoxes and riddles. These are not just intellectual exercises. They are fundamental questions that can make or break the possibility of time travel. First of all, this is the grandparent paradox. Imagine going back in time and not allowing your grandparents to meet. If they never meet, one of your parents will never be born, and therefore neither will you. But if you were never born, how would you even be able to travel through time? The grandfather paradox raises questions about causality and the nature of time itself. Some theorists suggest that such paradoxes can be resolved through the existence of parallel universes, where each solution generates a new timeline. Another confounding bootstrap paradox is named after the popular expression, pulling yourself up by your bootstraps. Imagine going back in time to give Shakespeare a copy of your works, which he then claims as his own. Where, in that case, did these works originate? The bootstrap paradox creates a closed loop of cause and effect with no apparent origin. It challenges our linear understanding of time and suggests that cause and effect may not be as simple as we think. Another paradox, the paradox of predestination, is when a time traveler's actions in the past lead to the very event he was trying to prevent. This raises questions about free will and determinism, and whether we can ever really change the course of history. The study of time travel paradoxes is not just a playground for philosophers. It's a serious area of research in physics and metaphysics. The resolution of these paradoxes may shed light on time travel. While we stand on the threshold of scientific discovery, the future of time travel remains a mystery shrouded in paradoxes, theories, and cosmic phenomena. What was once the realm of science fiction is gradually approaching the realm of real science. From cosmic strings to quantum entanglement, from spinning black holes to closed time-like curves, we explored the theories and possibilities that could one day make time travel a reality. Current research is paving the way for new experiments, new technologies, and perhaps even a new understanding of the structure of reality. But as we teeter on the edge of cosmic horizons, one question becomes more important than all others. Are we ready for what we might find? Time waits for no one, but what if we could wait for time? For years now, there's been a concept that defies the very laws of physics as we know them. A dream that has spawned countless stories and science fiction fantasies. This mystery is the search for a warp drive, a technology that could potentially allow us to travel vast distances in space, faster than light itself. Imagine a journey where time and space constraints yield to the power of human ingenuity, where the farthest corners of the universe suddenly become accessible. This isn't just science fiction. It's a puzzle that scientists have been piecing together for decades, ever since physicist Miguel Alcubierre proposed a theoretical model in 1994. Alcubierre's model, a bold combination of imagination and Einstein's theories, offers a way to bend the fabric of space-time itself. But what lies behind this bold idea? Is it a mere flight of fancy? Or could it be the key to unlocking interstellar travel? Today we explore the tangled web of problems and breakthroughs surrounding warp drive. From the mysterious nature of negative energy to the tangled horizon problem. So let's dive into the depths of one of the most intriguing scientific quests of our time. The quest for the warp engine. Science or fiction? In the heart of Mexico City, amidst the hustle and bustle of city life, a young mind was fascinated by the mysteries of the cosmos. We're talking about Miguel Alcubierre. Born in 1964, a physicist whose name has become synonymous with one of the most innovative ideas in theoretical physics. His journey began in Mexico and led him to the prestigious University of Wales, where he delved deeply into the fields of general relativity and cosmology. In 1994, while working at the Max Planck Institute for Gravitational Physics in Germany, Alcubierre made a breakthrough in world perception that challenged our understanding of space travel. Inspired by the iconic science fiction series Star Trek, he posed a bold question. Could the laws of physics allow for a real warp drive? Let's break down the Alcubierre drive. Imagine a spaceship that does not move through space in the usual sense, but sits in a space-time bubble. This bubble, or deformation bubble, is the key to the Alcubierre concept. According to Einstein's general theory of relativity, massive objects distort the fabric of space-time. Alcubierre hypothesized that if we could manipulate space-time in a controlled way, we could create a warp bubble. The space in front of the bubble is compressed, pushing the bubble forward. Behind it, space expands, pushing it from behind. Inside this bubble, the spaceship remains stationary, but the bubble itself moves, allowing the ship to move faster than light without violating the laws of physics. This idea doesn't involve moving the spaceship at high speed. Rather, it's about moving space around it. It's like putting a surfboard, a spaceship, on a wave warp bubble and letting the ocean, space-time, carry it. However, the Alcubierre model is not simply a manipulation of space. It requires exotic matter with a negative energy density to stabilize the warp bubble. This exotic matter is one of the many theoretical obstacles scientists face as they try to turn the Alcubierre drive from a fascinating theory into reality. Delving deeper into the practical aspects of the Alcubierre drive, we're faced with huge challenges that stand between theory and reality. The first of these is the scale of energy and mass requirements. It was originally thought that creating a warp bubble would require an amount of energy equivalent to the mass of the observable universe, an unimaginably huge amount, far beyond our current technological capabilities. However, the field of theoretical physics is constantly evolving. An outstanding achievement was when physicist Chris Vanderbroek proposed modifications to the shape of the warp bubble. These adjustments dramatically reduced the energy requirement to about the mass of 3 suns. Still a colossal amount, but a significant step down from the original estimates. The second major obstacle is the need for exotic matter and negative energy. In the Alcubierre model, this exotic matter is crucial to stabilizing the warp bubble and making it function as intended. Negative energy is a peculiar and controversial concept. It's a concept in physics that can distort the very fabric of space-time. It's not just the absence of energy, but an actual physical quantity with negative characteristics. In the context of Alcubierre drive, negative energy will counteract the effects of normal positive energy, creating the conditions necessary for the existence and stability of the warp bubble. Negative energy, in the context of Alcubierre drive, is indeed a complex and somewhat elusive concept in physics, and it's important to distinguish it from the more familiar concepts of gravitational potential energy. In classical physics, the concept of negative energy often refers to gravitational potential energy. For example, the gravitational potential energy of an object in a gravitational field, like a planet, is considered negative energy because it takes work to move the object from the source of gravity to a point where this energy would be zero, for example, to infinity. This form of negative energy is the cornerstone of our understanding of gravitational interactions in the universe. However, the negative energy required for the Alcubierre drive is different. In this context, negative energy refers to a hypothetical form of energy whose energy density is less than zero. It's not just an accounting tool or a way of describing potential energy in a gravitational field, but rather a real physical substance or field with exotic properties, such as repulsive gravitational effects. This type of negative energy is not something we observe or well understand in the context of known physics. However, the existence of negative energy and, by extension, exotic matter, remains a topic of intense debate and speculation in physics. Although phenomena such as the Casimir effect suggest the possibility of the existence of negative energy under certain conditions, harnessing it on the scale required for warp drive is a challenge. These challenges, the enormous energy requirements, and the need for exotic matter, underscore the monumental task of transforming Alcubierre drive from a theoretical model to a practical reality. They represent not just technological obstacles, but fundamental questions about the nature of the universe and our ability to manipulate its basic forces. As we move forward into the world of warp drive technology, we face another obstacle known as the horizon issue. This issue is at the heart of the Alcubierre drive design and poses serious problems for its practical application. In astrophysics, the horizon is often referred to as the boundary beyond which events cannot affect an outside observer. The most famous example is the event horizon of a black hole, the point of no return. Beyond this horizon, the gravitational attraction is so strong that nothing, not even light, can leave it. Similarly, in Alcubierre drive, the horizon is the boundary of a warp bubble. Inside this bubble, the spaceship is cut off from the rest of the universe, just as the interior of a black hole is isolated from the outside world by its event horizon. The horizon problem arises from the unique structure of the warp bubble itself. In the Alcubierre model, the spacecraft is located in a region of the space-time plane surrounded by a warp bubble that compresses space at the front and expands it at the back. This manipulation of space-time allows travel at speeds faster than the speed of light, but with a critical limitation. It isolates the spacecraft from the rest of the universe. Imagine being inside this warp bubble, the very mechanism that allows you to travel vast distances in space also prevents you from controlling the ship or interacting with the outside world. Communication signals, navigation commands, and even visual observations are all prevented by the bubble's boundary. Passengers and crew will not be able to control the spacecraft, correct its course, or even stop the journey once it's begun. The implications of the horizon problem are profound. It implies that a spacecraft driven by warp would essentially be traveling on a one-way, uncontrolled journey. This raises practical questions about using such technology for exploration or travel. How do we get to specific destinations? How do we avoid collisions with celestial objects or adjust our flight path to meet unforeseen circumstances? Moreover, this problem implies the need for a pre-established infrastructure, similar to an interstellar highway, with mechanisms to create and control the warp bubble from the outside. Such a requirement adds another layer of complexity to the already difficult task of realizing warp drive technology. While the Horizon problem represents a significant engineering challenge, it is important to recognize that it doesn't invalidate the fundamental scientific validity of the concept. Theoretically, the principles underlying the warp drive remain unchanged and plausible within the framework of the general theory of relativity. As we delve deeper into the complexities of Alcubierre drive, we encounter another major problem: the radiation problem. This problem is twofold. It involves both the accumulation of radiation at the front of the deformation bubble and the potential effects of Hawking radiation within the bubble itself. First, let us consider the radiation accumulating at the front of the warp bubble. As the bubble moves through space at a speed faster than the speed of light, it inevitably encounters interstellar particles and cosmic radiation. These particles and radiation, unable to bypass the warp bubble, accumulate near its front end. Such accumulation poses a significant risk. When the warp bubble slows or stops, the collected radiation and particles will be released in a burst of energy. The intensity of this release could be catastrophic, not only endangering the spacecraft and its passengers, but potentially damaging any nearby objects at the destination. Moving inside the warp bubble, we encounter the second aspect of the radiation problem: Hawking radiation. This theoretical radiation, predicted by Stephen Hawking, arises from the effects of quantum mechanics near the edges of black holes. In the context of Alcubierre drive, the intense warping of space-time around the edge of the bubble could create conditions similar to those at the event horizon of a black hole, potentially generating Hawking radiation. This radiation could have harmful effects on passengers inside the bubble, exposing them to high levels of energy and particles. The implications of these radiation problems are profound. Not only do they pose serious engineering and safety challenges, but they also raise questions about the feasibility of long-duration travel using Alcubierre drive. Ensuring passenger safety and spacecraft integrity in the face of these radiation hazards is a critical area requiring further research and innovative solutions. It is a challenge that requires ingenuity and a deeper understanding of the interplay between quantum mechanics, the theory of relativity, and the harsh reality of space travel. When we turn our eyes to the current state of research in warp drive technology, we find ourselves in the thick of scientific research. Recent years have seen a flurry of theoretical papers and articles that break new ground in this field. One notable development has come from the work of physicists who've been revisiting the energy requirements of the Alcubierre drive. Based on earlier advances that significantly reduce the estimated energy requirements, recent papers have proposed various methods to further optimize the geometry of the warp bubble. These improvements are aimed at making the energy requirements even more feasible, approaching the realm of possibility. Significant contributions to the field have been made by researchers such as Harold White, who was instrumental in the experimental work on the feasibility of deformation bubbles and space-time manipulation at the NASA Eagle Works laboratories. Another area of active research is exploring alternative theories that could circumvent some of the limitations of the Alcubierre drive. For example, some physicists are exploring the possibility of using solitons, solitary waves that retain their shape while traveling at a constant speed, as a basis for creating stable strain bubbles without the need for negative energy. There's also growing interest in the role of quantum mechanics in warp drive physics. Researchers are delving into the quantum aspects of spacetime and how they might affect warp drive mechanics. This includes studying the effects of quantum entanglement and the potential use of quantum fields to stabilize the warp bubble. recent theoretical advances also include the study of the effects of warp drive technology on causality and the fabric of spacetime. These studies are critical in addressing potential paradoxes and time travel scenarios, ensuring that the concept remains grounded in physical laws as we know them. Little by little, the dream of warp drive technology is moving ever closer from the pages of science fiction into the realm of scientific possibilities, driven by the tireless efforts of researchers around the world. As we ponder the future of warp drive technology, we find ourselves at a crossroad of assumptions and possibilities. The realization of warp drives, a concept once confined to the realm of science fiction, depends on several key developments and breakthroughs. First of all, the theoretical problems associated with warp drive technology need to be addressed. This includes finding viable solutions to the enormous energy requirements, the creation and stabilization of warp bubbles, and the safe management of radiation risks. Advances in areas such as quantum mechanics, exotic matter, and energy manipulation are critical to turning these theoretical possibilities into practical reality. Beyond the scientific and technical obstacles, the advent of warp drive technology brings with it many ethical and practical considerations. The ability to travel vast distances in space at unprecedented speeds would revolutionize space exploration, opening new horizons for humanity. However, with great power comes great responsibility. The ethical implications of such technology must be carefully considered. This includes the potential impact on space ecosystems, the responsibility to explore and possibly interact with extraterrestrial life, and equal access to this technology among nations and peoples. In practice, warp drive technology could lead to new methods of resource utilization, new ways of conducting scientific research, and even the possibility of interstellar colonization. This would fundamentally change our relationship with space, from one of exploration to one of habitation and utilization. For now, we look forward to a future in which stars are not just points of light in the night sky, but destinations within our reach. This future promises uncharted territories and unprecedented exploration, beckoning us to continue our quest for knowledge and discovery. There's an interesting mystery in our world, generated by the equations of Einstein's general theory of relativity. It's the theoretical analog of the black hole familiar to many. We call it a white hole. Imagine a region of space where, unlike an all-consuming black hole, nothing can penetrate. Instead, this cosmic anomaly defies our expectations by ejecting matter and energy, glowing violently on the dark canvas of space. In a universe governed by the concept of an arrow of time, where events flow from past to future, a white hole is a tantalizing paradox. It's like watching a space movie in reverse, where the rules of gravity and time seem to be rewritten. But are these celestial wonders just mathematical curiosities? Or do they hold the key to understanding the deeper truths of our universe? Let us delve into the mysteries of white holes, exploring their theoretical underpinnings, their enigmatic characteristics, and their potential role in the great history of the universe. In the early 20th century, Albert Einstein revolutionized our understanding of the universe by creating the general theory of relativity. This groundbreaking theory proposed a radical idea. Gravity is not a force pulling objects together, but rather a curvature of space-time caused by mass and energy. Imagine space-time as a fabric stretched like a cosmic trampoline. When an object of mass, such as a star or planet, lands on this fabric, it causes a dip. This curvature directs the motion of other objects, which move along curved trajectories in space-time. This is gravity, as Einstein envisioned it. Einstein's theory led to the prediction of black holes, regions in space where the gravitational pull is so strong that nothing, not even light, can escape. These cosmic giants form when massive stars collapse under their gravity, distorting space-time to the extreme. Introducing Carl Schwarzschild, a brilliant physicist who, while fighting in World War I, found an interesting solution to Einstein's equations. Schwarzschild's solution described space-time around a spherical, non-rotating mass, such as a star. Schwarzschild's work laid the foundation for understanding black holes, but it also hinted at something even more mysterious. If a black hole is a region from which nothing can escape, could its polar opposite exist? A region where nothing can enter, but only leave. This led to the birth of the concept of a white hole. Just as a black hole is the end point of gravitational collapse, a white hole can be thought of as a reverse black hole, a cosmic fountain ejecting matter and energy. However, unlike black holes, which have already been observed, white holes remain a theoretical concept, a tantalizing possibility in the vast cosmic mystery. In the field of astrophysics, the path from mathematical abstraction to physical reality is often long and difficult, and white holes are no exception. These theoretical entities arise from the complex equations of the general theory of relativity, the same mathematical structure that predicts the existence of black holes. The math of white holes is robust, but it's like a jigsaw puzzle with missing pieces. We understand their theoretical basis, but the real challenge is to relate these mathematical models to observable phenomena. Imagine a universe in which, instead of collapsing inward, a region of space-time does the opposite. It explosively ejects matter and energy. This is the essence of a white hole, a mirror image of a black hole, in which the flow of time and matter is reversed. But can these mathematical abstractions exist in our physical reality? The debate among scientists is ongoing and multifaceted. Some theorists suggest that white holes may be remnants of the early universe, exotic structures woven into the fabric of space-time itself. Others suggest they may represent the other end of a black hole, a kind of cosmic exit door from which matter and energy reappear after being swallowed up by the black hole. The novel idea of quantum gravity suggests that as a black hole evaporates over many epochs, losing mass, it may reach a point at which it can no longer sustain itself as a black hole. At that point, it may turn into a white hole, releasing the trapped contents back into the universe. However, there are serious problems with the physical existence of white holes. The laws of thermodynamics, especially the concept of entropy, presents a serious obstacle. Entropy, a measure of disorder, tends to increase in the universe. White holes, by their nature, decrease entropy, which contradicts this fundamental principle. Moreover, the stability of white holes is a controversial issue. Some theories suggest that if they did form, they'd be extremely unstable and would probably collapse almost instantaneously into black holes. In outer space, white holes represent one of the most enigmatic and paradoxical concepts. These mirror images of black holes have characteristics that challenge our traditional understanding of physics. Let us understand in more detail what is the concept of a white hole in theoretical physics. At the heart of a white hole is its event horizon, a boundary not of inescapability, as it is with black holes, but of impenetrability. This event horizon marks the point where matter and energy are ejected, creating a spectacle of cosmic proportions. Unlike a black hole, which takes over everything, a white hole is the source of the expulsion, the cosmic fountain from which matter and energy arise. One of the most intriguing aspects of white holes is the concept of time reversal. In the universe, time usually flows in one direction, from the past to the future. However, white holes seem to reverse this flow. It's like watching a space movie played backwards, where the usual rules of time and space are reversed. Deepening into the nature of white holes, we face a realm of paradoxes and problems. One of the most important is their connection with the previously mentioned entropy. According to the second principle of thermodynamics, entropy, or the measure of disorder, should always increase in a closed system. However, white holes seem to ignore this law, decreasing entropy and ejecting matter in an ordered state. This apparent violation of thermodynamic laws presents a serious problem for our understanding of physical processes in the universe. How can such an object as a white hole exist if it contradicts such a fundamental principle? Another paradox lies in the concept of the arrow of time. Where the universe moves inexorably forward in time, white holes suggest a scenario in which time can flow backward, at least from a certain point of view. This concept breaks not only our understanding of time, but also the very nature of causality in the universe. Let us summarize the characteristics of white holes, their event horizons, the expulsion of matter, and the concept of time reversal present a fascinating but paradoxical picture for theories that, while we're looking to solve these problems, white holes remain in the realm of theoretical physics. As we delve deeper into the mysteries of the cosmos, the concept of white holes invites us to rethink our understanding of the universe. These theoretical objects are not just surprising anomalies. They may have profound cosmological implications. Consider the Big Bang, the colossal explosion that marked the beginning of our universe. Some theorists suggest that this pivotal moment in cosmic history was not just a random explosion, but that the event may have been a white hole of unimaginable magnitude, an eruption of matter and energy that gave birth to the cosmos. This view offers a radical new interpretation of the origin of our universe, suggesting that white holes may play a role in cosmic genesis. Imagine a white hole not just as a theoretical construct, but as the very source of the creation of our universe. In this scenario, the Big Bang could be envisioned as a white hole of unfathomable scale, spewing out matter, energy, and space-time that subsequently evolved into the stars, galaxies, and planets we observe today. This view offers a radical rethinking of the Big Bang. Instead of an undefined singularity, we have a white hole, an entity defined by the laws of physics, albeit in a form that stretches our understanding to its limits. This white hole may have been the first spark that set the stage for subsequent cosmic evolution. If the Big Bang was indeed a white hole, it raises profound questions about the nature of our universe. What was the source of this white hole? Was it the result of a collapse of the universe from another dimension, or the result of processes beyond our current scientific understanding? This concept also changes our perception of time and causality. If the Big Bang was a white hole, it suggests the existence of a universe with a more complex timeline, in which the beginning and end of cosmic phenomena are intertwined in ways we've yet to understand. This idea of the Big Bang as a white hole organically combines with the Big Bounce theory, according to which the beginning of our universe may be the result of the collapse of the previous universe. It unites the idea of cyclical universes, suggesting that each cosmic end can give rise to a new beginning, similar to the explosive genesis of a white hole. The existence of white holes may also confirm the concept of parallel universes. If white holes can eject matter and energy, could they be a gateway to other universes? This possibility is related to the multiverse theory, which postulates the existence of multiple, possibly infinite universes, along with our own. In parallel universes, there may be different versions of physics, alternate histories, and perhaps even variations of ourselves. Another intriguing connection relates to wormholes, hypothetical tunnels in space-time. Theoretical models suggest that wormholes could link distant regions of space, and perhaps even different universes. If white holes are connected to wormholes, they could serve as cosmic portals, opening paths to remote corners of the universe or other dimensions altogether. This connection raises tantalizing questions about the nature of space and time. Could white holes and wormholes allow travel over vast cosmic distances, or even between different universes? Looking into the future of astrophysics, we see that at the moment there's a lot of scientific research in one way or another affecting the subject of white holes. But two research papers stand out among the rest, shedding light on the mysterious nature of these cosmic objects and offering new ideas and possibilities that could revolutionize our understanding of white holes. The first paper takes us on a journey to the very edge of black and white holes, exploring the close connections between them and refocusing on the physics occurring near their horizons. The authors introduce the concept of horizon-penetrating coordinate systems, a revolutionary approach that allows us to distinguish between the horizons of black and white holes. They differ from standard curvature coordinates in a small near-horizon region to emphasize the distinction between black and white horizons, which depends on near-horizon physics. This study suggests that black holes may not be the cosmic dead ends we once thought. Instead, they may be in quantum superposition with white holes, creating a scenario in which observed phenomena may hint at the existence of these theoretical white counterparts. The paper also delves into the role of quantum physics in these near-horizon regions, suggesting that quantum effects may dominate, leading to significant implications for our understanding of white holes. However, the authors emphasize that there's a problem in observational astrophysics, in which there is substantial observational evidence for black holes, but relatively weak observational support for white holes. Moving on to the second paper, titled New Black-to-White Hole Solutions with Improved Geometry and Energy Conditions, we find that the focus here is on the way to convert black holes into white holes, guided by the principles of quantum gravity. This study presents models in which the effects of quantum gravity prevent the formation of singularities inside black holes, providing a smooth transition to white holes. This solves the long-standing paradox of information loss by assuming that matter can pass through a black hole and appear in a white hole. The paper also explores geodesics within these models, confirming the completeness of particle trajectories in the transition from the black hole region to the white hole region. This supports the idea of a continuous, unimpeded flow of matter, changing our understanding of these cosmic phenomena. By integrating these theoretical developments with emerging technologies, we stand on the threshold of a new era in astrophysics. The future of white hole research promises to reveal new aspects of the universe, where the boundaries between quantum mechanics and general relativity are blurring. To summarize, we can say that the future of white hole research is very bright. Who knows? Perhaps very soon, we'll be able to discover indirect evidence for the existence of these intriguing objects. Our universe hides a mystery that's long captivated the human mind. A question that bridges the gap between the known and the unknown, the simple and the complex. Here on Earth, life thrives in a continuous movement of order and chaos. Every form of life is evidence of a hidden order, a pattern woven into the very fabric of existence, from the smallest microorganisms to the largest mammals. But what if the complexity of life, the very essence of our existence, could be explained not only through the lens of biology, but also through a mathematical framework? This is the territory of assembly theory, a groundbreaking concept that transcends traditional science. It's a journey into a world where math and biology converge to reveal the hidden architecture of life. Imagine a universe in which the secrets of life, from the simplest molecule to the most complex organism, are encoded in mathematical language and are waiting to be decoded, where the line between living and non-living is blurred, giving birth to new possibilities and new understanding. Let's explore how this revolutionary idea is changing our perception of life, evolution, and the cosmos itself. And maybe we can even get closer to answering the ultimate question: what is the true nature of life in the universe? Since the dawn of civilization, mathematics has been the language of the universe, a tool for deciphering the mysteries of nature. But how does this language of numbers and equations relate to understanding the very essence of life? At its core, assembly theory offers a simple but profound idea. The complexity of life can be measured and understood through a mathematical prism. Think of life as a jigsaw puzzle, where each piece represents a molecular building block. Assembly theory seeks to show how these pieces come together step by step to form the complex structures that define living organisms. Each step in this assembly process represents a leap of complexity, from simple atoms to complex proteins. The theory introduces the concept of the assembly index. The assembly index, the cornerstone of this theory, measures the number of steps required to build a biological structure. It's a numerical value that captures the essence of complexity by quantifying the immeasurable. But how does the standard model of physics fit into this? This standard model theory of physics describes the fundamental particles and forces that govern our universe. It seems completely separate from the complexities of biology. However, assembly theory bridges this gap. In the field of assembly theory, the standard model lays the foundation for understanding forces and interactions. It's a bridge between the microscopic world of quarks and leptons and the macroscopic world of living things. Another important element of the theory is the concept of studying dynamical systems, phase space. This is a mathematical concept used to describe all possible states of a system. In the context of assembly theory, phase space allows us to map the path of the assembly of life. From a single point representing the simplest form of life, phase space expands, branching out into almost infinite possibilities. Each pathway representing a different route that life can take. In this limitless mathematical landscape, the paths of evolution and its complexities unfold. This mathematical framework gives us a new perspective on the complexity of life. It's not just about the particles and forces described by the standard model, but how these elements combine and interact over time to create the diverse pattern of life we see around us. This is where the chaos of random molecular interactions gives way to the order of living structures. So let's ask ourselves this question: are the complexities of life simply the product of chance, or is there a deeper cause? Let us consider two sharply contrasting concepts: complexity and entropy. Entropy, a measure of disorder and randomness, seems to be at odds with the complexity we observe in life. How do these opposing forces coexist in the natural world? It's here that assembly theory offers a revolutionary perspective. So, central to assembly theory is the assembly index, a revolutionary tool designed to measure the complexity of life. Think of it as a cosmic ruler, measuring the steps required to assemble a biological structure from its simplest components. Imagine a single molecule as the starting point on this scale. As you move up the scale, each step represents a more complex assembly, from molecules to cells and beyond. The higher the index, the greater the complexity, and the less likely it is that the structure could have arisen by chance. Now let's delve into the interaction between entropy and complexity. Entropy, a concept rooted in thermodynamics, suggests that systems naturally tend toward disorder. However, life defies this tendency, evolving from simple origins to a variety of forms combined into the complex ordered structures we see today. How does assembly theory resolve this apparent contradiction? It suggests that life is inherently a process of overcoming entropy. Through the lens of the assembly index, we see the complexity of life is not a challenge to entropy, but a journey through it. Consider the early Earth, a primordial soup of simple molecules. Over millennia, driven by the laws of physics and chemistry, these molecules began to assemble into more complex structures. Each step along the way marked a victory over entropy, a step toward greater complexity in life. Rethinking evolution through assembly theory, we see it not as a mere biological process, but as a mathematical inevitability. The emergence and evolution of life became a story of increasing complexity, a story written in the language of mathematics. Let us now turn to a very trivial question, but one that shines in a new light. Are we alone? The search for extraterrestrial life has captivated our imagination for centuries. Now, thanks to assembly theory, we have a new tool in this cosmic quest. Assembly theory offers a unique approach to detecting alien life. It's not about scanning the sky for radio signals or analyzing light spectra for the presence of oxygen. Instead, it's about understanding the complexity of molecules and structures that may indicate life. Imagine scanning the atmosphere of a distant exoplanet or the surface of a moon in our solar system. Using assembly theory, we could analyze the molecular complexity of the samples in search of patterns that indicate the presence of life. The higher assembly index, the more likely it is that these molecules are the result of life rather than random processes. However, the road to discovering alien life is full of challenges and limitations. One of the biggest obstacles is our understanding of life itself. Our definition of life is based on what we know. Life on Earth. What if it doesn't meet our biochemical standards? Another problem is the vastness of space. The universe is vast, and our ability to explore it is limited by current technology. Even with the most sophisticated telescopes and probes, we can only analyze a tiny fraction of the cosmos. Moreover, assembly theory, while powerful, is still in its infancy. It's a new approach, and its application to the search for extraterrestrial life is uncharted territory. There are questions about its applicability and accuracy in different environments, especially those that are very different from terrestrial environments. Despite these problems, the potential of assembly theory in the search for alien life is enormous. It could redefine our understanding of life in the universe, opening new doors in astrobiology. So assembly theory offers a new way of looking at life, not just as a biological phenomenon, but as an emergent property of cosmic complexity. Imagine the early days of our planet, a world in motion, a crucible for the chemistry of life. Here in this chaotic environment, simple molecules began the journey of assembly, a process governed by the laws of physics and chemistry, but leading to something much deeper. Life, according to assembly theory, emerges when these molecular structures reach a level of complexity that allows them to store and reproduce information. This is where chemical memory, a crucial step in the evolution of life, comes into play. Chemical memory is the ability of certain molecular structures to retain structure. In other words, we can say this is the blueprint for life. In the world of assembly theory, this is where reproducibility becomes key. The ability to reproduce these patterns, to pass them on from generation to generation, is what drives the evolution of life. From the simplest RNA molecules in the primordial soup to the vast diversity of life we see today, each step in this evolutionary journey has been a step up the assembly index. Each increase in complexity represents a triumph over the entropy that governs the universe. But the story of the origin and evolution of life is not just a story of increasing complexity. It's also a story of resilience and adaptability. Life has found a way to thrive in the most extreme environments, from the depths of the ocean to the fringes of space. In the realm of scientific discovery, every new theory is scrutinized and debated. Assembly theory, a concept that promises to revolutionize our understanding of life and complexity, now stands at a crossroads, being questioned by critical voices such as Dr. Hector Zenel. The critique presented by Zenel raises fundamental questions about the future evolution of assembly theory. Covering an impressive 18,000 words, the article will require time and thought, taking approximately 1 to 2 hours of dedicated reading. This is not a cursory look at the topic, but a deep dive into the heart of the scientific debate. For those who are interested, we leave a link in the description to both articles, the study and the counter-arguments to it. Looking to the future, the role of assembly theory in scientific research remains uncertain. Will it be able to adapt and overcome these challenges, or will it remain a footnote in the history of science? Despite the disagreements, one thing is clear. The debates surrounding assembly theory have initiated a conversation about the nature of scientific discovery. They emphasize the need for transparency, rigor, and humility in pursuing knowledge. In the end, the impact of assembly theory on future research may not lie in its specific claims, but in the lessons it teaches us about the scientific process. As we explore the mysteries of life in the universe, such theories will come and go. But the quest for understanding, the quest to unlock the mysteries of our existence, will always remain at the center of the interest of scientific research. Imagine a colossal invisible force at the galaxy's heart, controlling its existence. This hidden conductor is none other than a supermassive black hole. Although they're often portrayed as chaotic, all-consuming monsters, these giants play a crucial role in the life cycle of galaxies. At the center of most large galaxies is a supermassive black hole whose gravitational pull is so strong that not even light can escape it. However, they actually do more than just absorb matter. They act as the heart and lungs of their galaxies, breathing life into the celestial environment in ways that are only beginning to be understood. Recent research shows that the jets of gas and radiation ejected from the poles of supermassive black holes are akin to the airways that feed our lungs. These jets create shock waves that oscillate, much like the thoracic diaphragm in our chest cavities, which moves to inflate and deflate our lungs. This respiratory system helps regulate the growth of galaxies, preventing them from getting too big and ensuring a delicate balance in the cosmic ecosystem. A simulation shows how a galaxy's heart and lungs in the form of gas plumes from a central supermassive black hole can prolong its life. If these supermassive black holes did not act as galactic regulators, the universe would be filled with zombie galaxies, huge clusters of dead or dying stars. The shock waves generated by black hole jets can prevent star formation by heating the surrounding gas, preventing it from cooling and condensing into new stars. This process may seem destructive, but it's necessary to maintain the health and longevity of galaxies. Today, we'll try to understand the mysterious nature of supermassive black holes, learn the profound impact they have on the universe, and by the end, we'll realize that even in the darkest corners of the cosmos, there is a heartbeat that connects us all. To fully understand the impact of black holes on galaxies, we need to understand their formation, types, and some key discoveries. Black holes can form in two main ways. The most common way is associated with the death of massive stars. When a star with a mass of about 8 to 10 times that of our Sun exhausts its nuclear fuel, a catastrophic explosion, known as a supernova, occurs. The core collapses under its own gravity, forming a stellar mass black hole. Such black holes usually have a mass several times that of the Sun. Another way is the direct collapse of massive gas clouds, which completely bypasses the star formation stage. This process can lead to the formation of black holes with masses from thousands to hundreds of thousands of solar masses. Such direct collapses are thought to have occurred in the early universe and were the seeds of the supermassive black holes we see today. The concept of black holes was first predicted by Carl Schwarzschild in 1915 as an exact solution to the equations of Einstein's general theory of relativity. These equations describe how matter forms the fabric of space and time. Schwarzschild's solution allowed us to discover regions where gravity is so strong that nothing, not even light, can escape it. The first black hole confirmed by observations was Cygnus X1. Discovered in 1964, this stellar mass black hole in the Milky Way was identified by X-ray emission that was caused by the accretion of material from a companion star. This discovery was the first convincing evidence that black holes are not just theoretical constructs, but real objects in the universe. Scientists have determined that a black hole consists of three main regions: the event horizon, the photon sphere, and the singularity. The event horizon is the boundary beyond which nothing can go once within its limits. The photon sphere is a region where gravity is so strong that light particles are forced to orbit. In the center, there is a singularity, a point of infinite density where the laws of physics known to us are destroyed. Black holes come in a variety of sizes. Stellar mass black holes are formed from collapsing stars and have masses several times that of the Sun. Supermassive black holes, located at the center of most galaxies, have masses ranging from millions to billions of solar masses. Intermediate mass black holes, which are less common, fall between these two categories and have masses between 100 and 100,000 solar masses. The 2019 Event Horizon Telescope collaboration has captured the first ever image of a black hole located in the galaxy M87. In this historic image, the black hole's shadow can be seen against a glowing accretion disk. The observation provided direct visual confirmation of theories about black holes and opened new possibilities for studying these mysterious objects. One of the most common and debated questions about black holes lately is whether they die. According to Stephen Hawking's theory, black holes can slowly evaporate over time through a process known as Hawking radiation. This occurs when pairs of virtual particles form near the event horizon, one falling into the black hole and the other flying out. Over an incredibly long period, this trickle of ejected particles can cause the black hole to lose mass and eventually vaporize. Although black holes are portrayed in science fiction, they're not cosmic vacuum cleaners that indiscriminately suck up everything around them. To hit them, objects must come incredibly close to the event horizon. In addition, although black holes have been proposed as potential wormholes or portals to other universes, these ideas remain speculative and are not supported by any observational data. Scientists estimate that the Milky Way alone contains more than 100 million black holes. Understanding the basics of black holes, how they form, their different types, and key discoveries lays a solid foundation for studying their profound impact on galaxies and the entire universe. So, although supermassive black holes are invisible, their presence is felt due to the enormous gravitational forces they exert on their surroundings. But how do these colossal formations arise, and what are their defining characteristics? Theoretically, a black hole is formed when a significant amount of matter is compressed into an incredibly small space, creating a gravitational field so powerful that it cannot escape. This concept, once considered too fanciful to be real, is now an accepted reality. Black holes, especially supermassive black holes, are scattered throughout the universe, and their number may be in the billions. Supermassive black holes, with masses millions or billions of times that of the Sun, are detected due to their gravitational influence on nearby stars. These stars orbit around the black hole much faster than they would around a normal object of similar size. By measuring these orbital velocities, astronomers can estimate the mass of the black hole. For example, the black hole at the center of our Milky Way, Sagittarius A, has a mass of about 4 million solar masses. Some supermassive black holes exceed even Sagittarius A. The dwarf galaxy Leo 1 is home to a black hole with a mass of about 3 million solar masses. In the neighboring elliptical galaxy Centaurus A, there is another black hole with a staggering mass of 55 million solar masses. And even more colossal is a black hole in the Abell 2261 galaxy cluster, estimated to have a mass of about 100 billion solar masses, although its exact location remains unspecified. These black holes, especially in active galaxies, behave differently. Surrounded by an accretion disk of rapidly spinning gas and dust, they can emit huge amounts of energy, sometimes outshining their entire galaxy. This very process was famously captured by the Event Horizon Telescope in 2019 when it imaged the accretion disk around the supermassive black hole in Messier 87, revealing the ominous shadow of a black hole with a mass of 6.5 billion solar masses. The formation of these supermassive black holes is the subject of intense study and speculation. Unlike the vacuum cleaners of science fiction stories, real black holes attract matter by gravity rather than by active suction. This gravitational attraction becomes unusually strong at close distances, but at greater distances, it behaves like the attraction of any other object of similar mass. According to one theory, the oldest supermassive black holes formed almost immediately by the gravitational collapse of massive gas clouds, containing as much matter as millions of stars. This direct collapse model suggests that such black holes could have formed in as little as 150 million years, a blink of an eye by cosmic standards. According to another hypothesis, primordial black holes born under the stressful conditions of the Big Bang served as seeds for subsequent growth. By studying these colossal formations, we gain insight into the fundamental processes that shape galaxies and, by extension, the universe itself. But what happens when two galaxies collide? It's not just a dramatic cosmic event, it's a transformational process that changes the very fabric of the universe. At the center of these galactic collisions are the same supermassive black holes, and their interactions produce some of the most energetic phenomena known. When galaxies approach each other, their central supermassive black holes begin to interact gravitationally, spiraling toward an inevitable merger. This process is not silent. It sets in motion vast amounts of ambient gas and dust, creating a turbulent environment ripe for extraordinary phenomena. Physicists have modeled these colossal mergers and found that as black holes spiral closer together, they can produce incredibly energetic jets of electromagnetic radiation. They fly out along the axis of rotation much more powerfully than those typically observed around isolated black holes. The cosmic show begins even before the black holes fully merge, giving astronomers a potential warning of these events. When these supermassive black holes finally collide, their jets combine into single high-energy bursts. These may be accompanied by less directional bursts, increasing the chances of detection. The merger process sets the surrounding plasma in motion, causing powerful jets that can theoretically be observed from billions of light years away. The detection of these cosmic events is not just exciting, it provides a unique opportunity to test the limits of Einstein's general theory of relativity under extreme conditions. The observation of these mergers can either strengthen the current understanding of gravity or open up new physics, potentially leading to alternative theories. Future missions such as the Laser Interferometer Space Antenna, or simply LISA, promise to expand our ability to pinpoint these mergers. LISA, a joint effort between NASA and the European Space Agency, will orbit the Sun and detect gravitational waves emitted by such mergers. Combining gravitational wave data with electromagnetic observations will allow precise localization and detailed study of these energetic events. Until such advanced instruments become operational, astronomers rely on existing observatories to detect electromagnetic jets. They provide a dynamic view of galaxy evolution, demonstrating how such mergers can dramatically change the structure and behavior of galaxies. But let's take a closer look at Sagittarius A, which is 4.3 million times the mass of the Sun. In mid-spring of this year, the giant of our galaxy revealed new secrets, thanks to the advanced observations of the Event Horizon Telescope. For the first time, astronomers have recorded polarized light around Sagittarius A, providing new insights into the magnetic fields surrounding this black hole. Polarized light is crucial to understanding these fields because it shows how light waves are oriented and allows us to understand the properties of the gas and the mechanisms at work in powering the black hole. Interestingly, the magnetic fields around Sagittarius A are strikingly similar to those observed around the much larger black hole in the galaxy Messier 87, which has a mass of 6.5 billion times that of our Sun. This similarity suggests that strong organized magnetic fields may be a common feature of all black holes, regardless of their size. The presence of such magnetic fields makes the possibility that Sagittarius A may contain a hidden jet intriguing. In other black holes, these fields drive powerful streams of matter. Although Sagittarius A appears relatively quiet, consuming a minimum of matter, the similar structure of its magnetic field hints at the possibility of a weak jettison that has yet to be observed. This new image of a black hole at the center of the Milky Way tells us that there are strong, swirling, and ordered magnetic fields near the black hole, explains Sarah Issa Un, study co-leader and NASA Hubble Fellowship Program Einstein Fellow at the Center for Astrophysics at Harvard and Smithsonian. These fields are crucial to how black holes interact with the gas and matter around them. It was the EHT, an array of telescopes around the world, that made these groundbreaking observations possible. By combining data from multiple telescopes, the EHT forms an Earth-sized virtual telescope capable of capturing unprecedented detail of black holes. Although Sagittarius A is closer to Earth, it presents a unique challenge because of its smaller size. The material swirling around it moves quickly, making it difficult to get clear images. In contrast, in the larger M87, the material moves more slowly, making it easier to observe. Overcoming these difficulties has provided invaluable data for comparing black holes at opposite ends of the mass spectrum. The observed similarity in the magnetic fields between Sagittarius A and Messier 87 suggests that the central black hole of our galaxy may possess a hidden jet. If such a jet exists, it would provide new insights into the behavior and evolution of black holes and the galaxies in which they reside. The observation of this jet would be a great discovery, linking Sagittarius A to the energetic processes that form galaxies. The discovery of such a jet will greatly expand our understanding of how black holes affect their surroundings. Jets can expel gas and dust, affecting star formation and the overall evolution of galaxies. By comparing different black holes, astronomers will be able to identify the universal principles that govern these mysterious objects. Studying our own supermassive black hole allows us to root these abstract concepts in a familiar context, bringing distant space closer to home. The influence of supermassive black holes extends far beyond their gravitational effects. Relativistic jets can have a dramatic effect on the formation and evolution of galaxies, affecting everything from star formation to the distribution of gas and dust. A striking example of the influence of black hole jets is the Teacup Galaxy, located at a distance of about 1.3 billion light-years from Earth. The Teacup Galaxy got its name because of its peculiar handle structure, which was formed due to the activity of a relativistic jet from its central supermassive black hole. This galaxy is a vivid example of how even low-powered jets can significantly affect the environment. Even in the case of radio-quiet galaxies, jets can redistribute and disrupt the surrounding gas, and this will have an impact on the galaxy's ability to form new stars. Recent observations with the Atacama Large Millimeter Array have shown that jets in the Teacup Galaxy, although relatively weak, move, heat, and accelerate the galaxy's gas. Even in the case of radio-molten galaxies, jets can redistribute and disrupt the surrounding gas, and this affects the galaxy's ability to form new stars, explains Cristina Raus Almeida, an astronomer at the Instituto de Astrofísica de Canarias. The effects of these jets do not always occur head-on. The study found that the most significant effects in the Teacup Galaxy occur perpendicular to the direction of the jets. This lateral turbulence is caused by shock waves generated by the jet bubble, which heats and inflates the gas. These interactions can prevent star formation by preventing the gas from cooling and collapsing into new stars. While strong jets can heat the gas in galaxies to such an extent that they slow its growth, preventing the formation of new stars, weaker jets, such as in radio-quiet galaxies, also play an important role. These jets can still stir up the gas in a galaxy, causing it to move and redistribute. Such activity can lead to the formation of new structures within the galaxy and affect its long-term evolution. Understanding the influence of these jets allows astronomers to piece together the complex puzzle of galaxy formation. Supermassive black holes are an integral part of the life cycle of galaxies, from the dramatic changes caused by powerful jets to the more subtle but significant effects of weak ones. Stay tuned to explore together the forces that shape our universe. What lies beyond the observable universe? As we gaze into the celestial tapestry, our understanding stretches from the familiar glow of our solar system to the enigmatic dark spaces that challenge every truth we hold dear. From the rudimentary lenses of Galileo, which first charted the moons of Jupiter, to the intricate orbits of modern space telescopes capturing distant galaxies, our tools for probing the cosmos have evolved dramatically. Yet each discovery peels back only a layer of more profound mysteries ahead. The intriguing presence of dark matter and dark energy suggests that much of the universe is shaped by substances and invisible forces, dictating the speed at which galaxies rotate and the universe expands. But could there be more than our universe? The theory of the multiverse proposes a spectrum of possibilities where different laws of physics may apply. Each discovery, from black holes bending the fabric of space-time to gravitational waves echoing through the cosmos, is a puzzle in understanding the broader cosmic picture. These cosmic phenomena challenge our perceptions and invite us to contemplate the more profound mysteries that define our universe and possibly others. Are we ready to redefine our understanding of the cosmos and accept the boundless realms of the multiverse? This narrative challenges our perceptions and invites us to explore the profound implications of what lies beyond the observable universe. As humankind has plumbed the depths of the universe, it's begun to encounter phenomena that our traditional understanding of physics could not describe. Among them are dark matter and dark energy, components of the cosmos that remain invisible to our telescopes, but profoundly affect the structure and fate of the universe. The mystery of dark matter first arose from the study of the rotation curves of galaxies. According to Newtonian mechanics, stars at the galaxy's outer edges should rotate slower than in the center, like the planets in our solar system. However, observations have shown that this is not the case. Instead, the rotation rate of stars and galaxies remains constant, suggesting that there is an invisible mass exerting an additional gravitational force. This matter, detectable only through its gravitational influence, forms the entire skeleton of the universe. Turning our gaze from the hidden mass inside galaxies, we encountered an even more elusive component: dark energy. This mysterious force drives the universe's accelerating expansion, a phenomenon first detected by the strange behavior of distant supernovae. Instead of slowing down, as one might expect from the gravitational pull of the entire universe's mass, its expansion is accelerating. Among these expansive forces, black holes anchor the cosmic drama. Born from the collapsing cores of massive stars, these gravitational giants warp space-time to the point where even light cannot escape their grip. The first direct image of a black hole's event horizon revealed a universe stranger and more fantastic than we could have imagined. And rather than providing new answers, it only added questions to those already existing. However, the interaction of these cosmic giants is not silent. When black holes merge, they send gravitational waves throughout the universe, rips in space-time that we've only recently begun to detect. Observatories like LIGO and Virgo are capturing these waves, giving us new insights into some of the most violent events in the universe. Gravitational waves have opened a new channel through which we can explore the cosmos, complementing the electromagnetic spectrum that's been our primary window into the universe. By analyzing these waves, scientists can unlock the secrets of black hole masses, rotations, and merger details, enriching our understanding of the fundamental physics that governs the most extreme objects in the universe. But this is only part of humanity's quest to understand the cosmos's cruel mechanisms and find potential cradles for life throughout the universe. The search for exoplanets and the search for extraterrestrial intelligence represent two journeys into the unknown, guided by our deep curiosity about the cosmos. The discovery of myriad worlds orbiting stars within our galaxy has opened a new chapter in our understanding of the universe, expanding our horizons beyond our solar system to include many planets with conditions as diverse as those on Earth. Each discovery, from the sultry surfaces of hot Jupiters to the potentially habitable conditions on super-Earths, becomes the basis for a broader story about our place in the universe. With its unprecedented observational capabilities, the James Webb Space Telescope allows us to peer into the atmospheres of these distant worlds, analyze their composition, and look for signs of life. This bridge to the stars is not just about discovering new planets. It's about understanding the conditions that can support life, a question that naturally extends to the search for signals from civilizations beyond our planet. Meanwhile, an initiative known as the Search for Extraterrestrial Intelligence, or SETI, has continued for decades to explore the silent expanse of space, listening for faint whispers of civilizations that may exist in these distant worlds. Use of technologies covering a vast electromagnetic spectrum, SETI's efforts underscore the enormity of our search and the tantalizing possibility that we are not alone. At the heart of SETI's theoretical foundation is the Drake equation. Formulated by astronomer Frank Drake in 1961, the equation offers a way to estimate the number of active, friendly, extraterrestrial civilizations in the Milky Way galaxy. The equation considers factors such as the star formation rate, the fraction of stars with planetary systems, the number of planets on which ecosystems can develop, and the likelihood of intelligent life. The equation highlights the vast number of unknowns in this search, from the fraction of habitable planets with life to technological civilizations' longevity. Nevertheless, searching for the potential for life in space is only the beginning. The deeper we delve into the mysteries of the cosmos, the more our knowledge expands, and the more questions arise. The constant change in our understanding of the cosmos lays the groundwork for considering even more possibilities. The enigmatic phenomena discovered in the course of these investigations, the invisible scaffolding of dark matter, and the pressure of dark energy on the expansion of the universe, provide the basis for considering the multiverse not as science fiction, but as a plausible structure that can explain mysteries that remain beyond our current scientific reach. Our current search, limited to the observable universe and based on our understanding of life on Earth, can only scratch the surface of what's truly possible. Multiverse theory opens up an even more comprehensive range of possibilities, reaching beyond our observable universe into realms where the fundamental laws of physics may be radically different. The Drake equation, which is the basis for our search for extraterrestrial intelligence by estimating the number of friendly civilizations in our galaxy, operates within the physical laws of our universe. However, if we embrace the multiverse theory, the equation may be just one of countless ways to understand the potential for life in a more extensive and diverse multiverse landscape. In general, the multiverse concept pushes the boundaries of our cosmic understanding into new, uncharted territories. It suggests that our universe, as vast and complex as it is, may be only one of a vast number, perhaps an infinite number, of universes existing parallel to our own. The seeds of the multiverse theory are in quantum mechanics and cosmology. With its probabilistic nature, quantum mechanics introduces the idea of parallel outcomes arising from the same quantum events. If we apply this principle to cosmological scales, we can assume that in the universe, each possibility is realized in its own separate cosmos. Cosmic inflation, a theory describing the exponential expansion of the early universe, provides another basis for a multiverse. Inflation suggests that bubbles of space may have formed, each expanding into its universe with a larger multiverse. These bubbles may have different properties and physical laws dictated by the nature of the inflationary field in each region. Most conceptions of the multiverse are not monolithic. They include several models, each with its implications for our understanding of reality. Bubble universes emerging from the theory of cosmic inflation. Bubble universes are distinct regions within a large space, each having undergone its inflationary expansion. These universes can radically differ from our own, with different physical constants and laws. Quantum multiverses, based on quantum mechanics. This interpretation asserts that each quantum decision point generates a new parallel universe. Every conceivable outcome of any event generates its universe, resulting in an almost unimaginable variety of parallel histories and futures. Mathematical universes. This model assumes the existence of all mathematically possible universes. If physical laws, as we understand them, are merely mathematical structures, then all structures that can be described mathematically exist as tangibly as our universe. For example, let's look at the type of multiverse classified by astrophysicist and cosmologist Max Tegmark. Level 1. The infinite universe. At the first level of the Tegmark model, the universe extends infinitely beyond the observed cosmos. At this level, it's assumed that our observable universe, 92 billion light-years in diameter, is just an infinitesimal particle in an increasingly vast cosmic landscape. Every structure, event, and variation is infinitely repeatable in space, suggesting that our duplicates exist somewhere in similar conditions, if not identical. Level 2. The post-inflationary multiverse. The second level of Max Tegmark's multiverse model explores the realm where individual universes arise from their own unique Big Bang events. This classification is rooted in the concept of chaotic inflation, which assumes the existence of a cosmos in which our universe is just one of countless others, generated by inflationary bubbles. Chaotic inflation assumes that the rapid expansion of the universe, which we think of as the Big Bang, is not a single event, but a common phenomenon throughout cosmic history. In this model, inflation never stops completely. It stops only locally, like bubbles forming and separating in boiling water. Each bubble becomes a new universe with potentially different physical constants. In these individual universes, the fundamental constants and even the laws of physics can change from bubble to bubble. These differences can lead to universes that are radically different from our own. For example, gravity may be stronger in one universe, affecting the formation and evolution of stars and galaxies. In another, different levels of electromagnetic forces may change the chemistry of life, of course, if life is even possible in it. To understand the implications of changing these constants, imagine throwing a ball in a universe where gravity is 3 times stronger than it is here. The ball would not fly as far or as high, fundamentally changing games like basketball or soccer. If you extend this analogy to celestial mechanics, you can imagine that planets could orbit much closer to their stars, and stars could be smaller and burn up faster. If physical constants can vary so widely, then the conditions that led to the emergence of life on Earth are just one possibility of a vast cosmic lottery. Each universe may be a unique experiment to explore the possibilities of physical reality. Although second-level multiverses differ fundamentally in their constants, they share a common link with their first-level multiverses, where all the laws of physics are constant, but the initial constants vary. This multi-level structure of the multiverse not only expands our understanding of what's possible, but also provides a basis for understanding the incredible variety of conditions under which universes can form. Level 3. The Many Worlds Interpretation of Quantum Mechanics. Perhaps the most disconcerting of Tegmart's levels, the third level, introduces the concept of quantum mechanics into the multiverse theory. According to the interpretation of multiple worlds, every possible outcome of every event defines or gives rise to a new world or universe. This level assumes infinite timelines and possibilities where each conceivable scenario takes place in its own universe. Imagine a simple everyday decision, such as turning left or right on your way to work. In the Many Worlds interpretation, each choice results in a branching universe. One version of you turns left, while another version turns right in a parallel universe. These universes exist simultaneously, but do not interact with each other, and each follows its path of reality based on that single quantum decision. Another example is the flip of a coin. In our everyday experience, the coin falls either heads or tails. However, in the context of the Many Worlds interpretation, at the moment of the coin flip, the universe is split into two, one where the coin falls heads and one where it falls tails. Each outcome exists in its separate universe, and the consequences of this simple event spread outward, affecting further events in each respective universe. However, this interpretation goes beyond human-scale events and encompasses all quantum events in the universe. For example, the same decay of a radioactive atom, a fundamentally random process at the quantum level, would cause the universe to split into one in which the atom decayed and one in which it did not. Each of these universes would continue to evolve independently, accumulating its unique history. The fascinating aspect of this level of the multiverse lies not only in its scientific implications, but also in the way it reflects the complexity of human choices and the inherent unpredictability of life. Just as we can ponder what-if scenarios regarding our past decisions, the interpretation of many worlds realizes these alternatives in countless parallel universes. Level 4. Ultimate Ensemble. The fourth level of Max Tegmart's multiverse classification represents the most radical and profound conception of all possible universes. In this model, known as the mathematical universe hypothesis, reality is viewed as a landscape of mathematical structures. Each structure defines a separate universe, distinguished not only by physical constants or laws, but also by potentially entire mathematical structures. According to the hypothesis of mathematical universes, our physical world is not just described by mathematics, it is mathematics. This means every conceivable mathematical structure exists as a physical reality somewhere in a multiverse. These universes may function based on entirely different mathematical rules than the ones we know and understand. To illustrate this profound concept, let's take a simple object like an orange. Imagine holding an orange in your hand. It's familiar and tangible, but this orange is a set of mathematical properties at its core. The shape of the orange, the ideal sphere, is not just a physical form, but a geometric expression that describes contours and volume, defining how the orange exists in space. Now, think about the orange color that we see. This bright hue is not just a random feature. It results from light interacting with molecules on the orange's surface that absorb and reflect light at specific wavelengths. Because the science of light, optics, is deeply mathematical, it relies on equations that describe how light behaves when it encounters an object. Even the taste of an orange, the combination of sweetness and acidity, is driven by chemical reactions that can be quantified and predicted with mathematical precision. The concentrations of sugars and acids are subject to chemical laws. essentially mathematical relationships that determine how substances interact. Every aspect of an orange, from its growth to the sensations it evokes when we eat it, can be described using math. In this way, this simple fruit becomes a small, tangible proof of a much larger truth. Our entire universe, from the smallest atom to the largest galaxy, can be part of a grand mathematical structure. If we accept that every mathematical structure corresponds to a physical universe, the implications for science and philosophy are enormous. It implies that any universe that a consistent set of mathematical rules can describe exists as surely as our own. It implies that universes with radically different properties that defy our physical intuition are just as real as our own. Consider a universe in which the dimensions of space and time are not 4, as in our visible universe, but 5, 10, or even more. The behavior of particles and forces in such a universe could be radically different, changing the process of matter formation and evolution. Or imagine a universe governed by a different type of geometry, where the shortest path between 2 points is not a straight line, but some other curve, which radically changes the structure of the universe and the life it can support. Level 4 is connected to the other levels of the multiverse, providing the ultimate framework, while levels 1 to 3 deal with the universes that differ in initial conditions, physical constants, or quantum results. Level 4 encompasses all possible mathematical realities. It offers a cosmos where the boundaries of possibility are limited only by the limits of the mathematical imagination. The implications of the multiverse theory go beyond physics and into philosophy, forcing us to think about the most fundamental concepts of reality, causality, and existence. If the multiverse is real, it means that with all its complexity and beauty, our universe is just one of countless others, each with its own history, laws, and perhaps even life forms. In the scientific realm, the multiverse theory raises profound questions about the nature of scientific inquiry and evidence. Since other universes in the multiverse are, by definition, beyond our observation, the theory walks a fine line between physics and metaphysics, forcing us to reflect on views of the principles of empirical science.
That's one small step for man, one giant leap for man.
As we ponder the vastness of the universe and the possibility of countless worlds in the multiverse, our quest for space exploration continues to propel us forward. The next chapter in human space exploration is being written now, with ambitious programs and missions that aim to expand our presence beyond Earth, back to the Moon, onward toward Mars, and eventually beyond our solar system. In conjunction with international and commercial partners, NASA's Artemis program marks a major milestone in our efforts to explore the Moon. Named after Apollo's twin sister, the Artemis program aims to return humans to the Moon by the mid-2020s, with the lofty goal of a sustained human presence there by decade's end. Unlike the Apollo missions, which were short-term visits, Artemis envisions a long-term presence of humans and robots on the Moon, utilizing its resources and using it as a testing ground for technologies needed for deeper space exploration. The Artemis architecture includes Gateway, an orbital lunar outpost that will support long-term human missions to the Moon and serve as a transfer point for missions to Mars and beyond. Gateway will facilitate scientific research, provide a platform for testing new technologies, and usher in a new era of the international cooperation in space. In turn, the red planet Mars has long captured our imagination as the next frontier for human exploration. Based on decades of robotic exploration, plans for manned missions to Mars are taking shape to send astronauts to Mars in the 2030s. These missions will require improvements in life support, propulsion, and habitat technologies, and a better understanding of the psychological and physiological effects of long-duration space travel. Human missions to Mars will aim not only to answer fundamental questions about the planet's history and geology, but also to search for signs of past life, test the possibility of existence on Martian soil and lay the groundwork for future colonization. While the Moon and Mars are within our reach, the ultimate challenge is interstellar travel, expeditions to other star systems. One of the most visionary projects in this area is Breakthrough Starshot, an initiative to build a fleet of light-sail spaceships capable of traveling to our nearest stellar neighbors, such as the Alpha Centauri system. These spacecraft could theoretically be accelerated to a significant fraction of the speed of light, allowing them to reach Alpha Centauri in just over 2 decades after launch. Such missions could provide invaluable data on other star systems and potentially habitable exoplanets, paving the way for future interstellar exploration. The journey to the Moon, Mars, and ultimately to the stars is not just a series of missions, but a continuation of our fundamental quest to explore, to understand, and connect with the universe around us. Even stepping into the next chapter of human space exploration can push the boundaries of our technological and scientific capabilities and inspire future generations to dream of the possibilities that lie beyond our cosmic horizon. Imagine a line, a simple, unbroken line stretching into infinity. This line, in its purest form, represents the first dimension, a realm of length but without depth, a universe infinitely long but impossibly thin. Now, let's broaden our perspective, introduce a second line intersecting the first, and suddenly we're in the realm of the second dimension, a plane where length and width interact in harmony, but depth remains a variable alien to them. As we go one step higher, we find ourselves in the familiar embrace of the third dimension. This is where depth comes in, adding volume and substance to our world. Buildings rise, valleys deepen, and the universe takes on texture and shape. But what if we could add another layer? Time is the elusive fourth dimension that permeates our three-dimensional space. Invisible but omnipresent, it dictates the rhythm of our lives, a continuous thread connecting each previous moment with the current one and the current one with the next. In this realm, our understanding of reality becomes more complex and broader. Here, the very fabric of the universe reveals its complexity, hinting at dimensions beyond our sensory perception. However, nature hints at even more complex dimensions. In the field of physics, theories suggest the existence of dimensions beyond our perception, necessary for the fundamental forces that govern the universe. These higher dimensions, although beyond our sensory perception, are crucial to understanding the structure of the cosmos. Join us as we try to unravel their mysteries together today, one dimension at a time. In a historical context, the concept of measurement permeates all human thought, from the abstract reflections of ancient philosophers to the revolutionary discoveries of modern physics. Philosophers once pondered the nature of existence, laying the foundations for our understanding of space. In their discussions, they questioned the very essence of reality, imagining realms beyond the tangible. As the centuries passed, these philosophical speculations paved the way for more structured inquiry into the nature of the universe. Meet the visionary Hermann Minkowski, who irrevocably changed our understanding by proposing that time and space are not separate entities, but intertwined dimensions that form the fabric of space-time. Albert Einstein, in turn, based on the foundation laid by Minkowski, presented the revolutionary theory of general relativity, restructuring our understanding of gravity, space, and time in a single continuum, forever changing the course of physics. Thus, from the philosophical quest of the ancient thinkers to the scientific revolutions sparked by Minkowski and Einstein, the journey through the evolution of spatial thinking reveals a relentless quest to comprehend the true nature of our universe. So, over time, we've come to realize that to truly comprehend the fabric of our reality, we must go beyond the three tangible dimensions into the realm of the fourth dimension, time. The concept of time as a dimension is both profound and persuasive, defining our existence and the universe as a whole. Unlike the three spatial dimensions, time has a direction. It moves inexorably forward, from the past through the present and into the future. This unidirectional flow of time distinguishes it from space, bringing to the universe a temporal structure that is fundamental to our understanding of reality. To illustrate the importance of time as a dimension, consider a simple everyday scenario: organizing a meeting. When we suggest that someone meet at a certain place, we unconsciously navigate the three basic spatial dimensions to determine where. It makes sense that if we arrived at different places, no meeting would take place. However, the when, the dimension without which the meeting will not take place, is no less important. That is, coming with your friend to the same place but at different time intervals, you'll not be able to see each other. This intertwining of space and time is manifested in the concept of world line, the path that an object or person takes through space-time, thus representing its history and future. The idea of world lines provides a vivid illustration of how events are linked together in the fabric of space-time. For two people to meet, their world lines must intersect at a precise point in both space and time. This intersection is not just a spatial coordinate, but a space-time coordinate, the only point in the vast continuum of the universe where both where and when coincide. This principle applies not only to simple encounters but also to the fundamental workings of the cosmos. Celestial bodies from planets to stars trace their own world lines through space-time, their paths determined by the interplay of spatial positions and temporal moments. For example, the Earth's orbit around the Sun is not just a path through space, but a continuous journey through time, with each point in the orbit representing a unique moment. The integration of time as a dimension has a profound effect on our perception of the universe. It forces us to look beyond static images of space to the dynamic unfolding of events. Time allows us to understand the universe not as a set of individual moments, but as a continuous narrative where cause and effect bind our reality into a coherent whole. The inclusion of time as a dimension has catalyzed major advances in physics, particularly through Einstein's theories of relativity, which we've already mentioned. These theories not only deepened our understanding of the cosmos, but also paved the way for new research in quantum mechanics and cosmology. Einstein's revelation that time is relative, it slows down or shrinks depending on the velocity of an object, challenged the idea of a universal clock. This concept, rooted in the special theory of relativity, illustrates how the passage of time changes for observers in different reference frames. This phenomenon is confirmed by experiments, for example, with atomic clocks on fast-moving airplanes. In quantum mechanics, time as a dimension underlies the evolution of particle state governed by the Schrödinger equation. This basis is important for understanding phenomena such as entanglement and superposition, where the time dimension provides a probability distribution of outcomes. Going beyond the fourth dimension opens the door to a realm where our everyday experience and the laws of physics as we know them are fundamentally challenged and expanded. In search of a unified theory that harmonizes the principles of quantum mechanics and the general theory of relativity, physicists have ventured into the theoretical landscape of higher dimensions, where the fabric of the universe becomes even more intricate and mysterious. The fifth dimension and beyond are not just speculative constructs, but important components in the quest for a deeper understanding of the universe. In theories such as string theory, These higher dimensions offer solutions to some of physics' most challenging mysteries, including the unification of fundamental forces and the nature of gravity at quantum scales. The difficulty in visualizing higher dimensions is that our perception is inherently three-dimensional. Therefore, analogies become an invaluable tool. One of the classic analogies to help understand the concept of higher dimensions is to imagine the perspective of a two-dimensional being, often called a flatlander, living in a flat two-dimensional world. This being can move forward and backward, left and right, but has no concept of moving up and down because these dimensions do not exist in its two-dimensional experience. Imagine a three-dimensional sphere passing through this two-dimensional world. To a flatlander, the sphere would first appear as a dot when the sphere is just touching the two-dimensional plane, gradually increasing into a circle as more of the sphere passes through the plane, and then decreasing again to a point as the sphere leaves the plane, before disappearing altogether. A two-dimensional being would perceive this event as a circle that appears out of nowhere, changes size, and then disappears, without realizing what three-dimensional object is causing the phenomenon. String theory, the leading candidate for a unified theory, posits that particles are not the individual points we see them to be, but tiny vibrating strings, whose modes of vibration determine the properties of the particles. This theory requires the existence of more than 4 known dimensions. In fact, it suggests that there may be as many as 10 or 11. These additional dimensions are compacted or convolved so that they are imperceptible on our scale, like the sphere in the flatlander example. In the 5th dimension, we encounter a space containing all possible universes that start from the same initial conditions as our own universe. Imagine a tree, each branch representing a different decision or outcome leading to a different reality, all coming from the same trunk. Just as a person standing at the base of the tree can choose which branch to climb, a being with access to the 5th dimension can explore these alternate realities, each a variation of our own universe, but with slightly different outcomes. The ascent to the 6th dimension opens a plane containing all possible universes with the same initial conditions as ours, but with any possible set of laws of physics. If we think of each universe as a sheet of paper, the 6th dimension would be like a stack of such sheets, each representing a different universe. A being capable of traveling through the 6th dimension could hop between these universes, learning the different outcomes and laws governing each reality. The 7th dimension extends this concept to include universes that start from different initial conditions. To use a library analogy, each book represents a different universe. The 7th dimension encompasses the entire library, offering not just different stories, universes with the same initial conditions as ours but with different outcomes, but completely different genres, universes with different initial conditions. A 7-dimensional being could move through this library, experiencing an infinite number of universes, each with its own unique initial conditions and physical laws. In the 8th dimension, we find a web of all possible universes, each with its own initial conditions and laws of physics, as well as all possible variants of their development in time. Imagine a huge web where each thread represents the timeline of a separate universe, and each node where the threads cross represents an important event that could lead to the branching of new universes. The 8th dimension encompasses this entire web, allowing you to travel between any nodes, exploring the connections between different universes and their history. As we approach the 9th dimension, we encounter all possible laws of physics and initial conditions that have existed or will ever exist. This dimension can be compared to the art of origami, where a single piece of paper can be folded into numerous shapes. Each fold represents a change in the initial conditions or laws of the universe. And the ninth dimension includes all possible combinations of folds, resulting in all conceivable and inconceivable universes. A being living in the ninth dimension will not just have absolute freedom to cross the boundaries between all possible realms of reality, it will experience all existence and all its possible variations. The 10th dimension is the pinnacle of the hierarchy of dimensions, where all possible outcomes, realities, and existences converge. It's the space that encompasses all conceivable and inconceivable timelines for every conceivable universe, effectively encompassing all possibilities of existence and non-existence. This concept can be visualized as an infinitely complex branching tree or network, where each branch represents a different outcome or timeline. And all branches ultimately converge at one point, the 10th dimension. Visualizing the 10th dimension is challenging because of its abstract nature. One approach is to use the analogy of a tree, where each branch represents a different timeline or universe, and each leaf represents a possible outcome within that universe. Moving from trunk to leaves, we move from the initial conditions of the universe, lower dimensions, through the various choices and events, higher dimensions, that lead to all possible outcomes. The 10th dimension represents the point where all these possibilities come together, the singularity of infinite potential outcomes. It suggests a cosmos in which all possible outcomes not only can happen, but happen in some timeline or universe in the 10th dimension. The concept itself invites us to reflect on the vastness of possibilities that lie beyond our observable universe. It raises questions about fate, choice, and the underlying structure of the cosmos, prompting a broader exploration of potential realities that may exist beyond our immediate perception. The exploration of higher dimensions beyond our familiar three-dimensional space and fourth-dimensional time has profound implications for both physics and cosmology. Not only is this field of study designed to challenge our fundamental understanding of the universe, but it may also hold the key to uniting the disparate forces of nature, potentially solving some of cosmology's most enigmatic puzzles. Recognizing the existence of higher dimensions plays a key role in the search for a theory of everything, a single framework that will seamlessly unify general relativity and quantum mechanics. Currently, these two pillars of modern physics describe the cosmos on very different scales and in seemingly incompatible terms. General relativity perfectly explains the gravitational interaction of massive celestial bodies, while quantum mechanics reveals the intricate world of subatomic particles. Higher dimensions may also offer new insights into cosmological mysteries, such as dark matter, dark energy, and the nature of black holes. For example, some theories suggest that what we perceive as dark matter may be gravitational effects from matter in parallel branches, a concept from M-theory, which suggests multiple parallel membranes, or branes, as fundamental components of the universe, each potentially containing another universe in higher dimensions. Looking to the future in the field of energy, mastering the intricacies of higher dimensions could pave the way to harness forms and mechanisms of energy that we cannot now even imagine, and potentially lead to the creation of clean, virtually inexhaustible sources of energy. Similarly, the field of space travel could be revolutionized by a better understanding of the fabric of space-time, perhaps eventually enabling warp drives or other forms of faster-than-light travel. Concepts that are currently in the realm of science fiction but could be theoretically plausible within higher dimensions. The search for higher dimensions is already underway. Researchers are exploring the subatomic world with particle gas pedals such as the Large Hadron Collider at CERN, looking for evidence of additional dimensions and the particles that may inhabit them. This experimental work is complemented by theoretical studies that delve physicists and mathematicians into the abstract realms of high-dimensional spaces. As we complete our journey through the dimensions, from the simplicity of a line extending into infinity to the unfathomable complexity of the 10th dimension, we're faced with the inherent challenge of visualizing spaces beyond our three-dimensional experience. Through math, we can describe properties and relationships within higher dimensions, and physics offers theories such as string theory and M theory that hint at the existence of these additional dimensions. Animation such as tesseracts allows us to conceptualize high-dimensional shapes and their projections or shadows in lower dimensions. Further exploration of higher dimensions promises to revolutionize our understanding of the universe. Just as the transition from a flat Earth to a spherical Earth many centuries ago broadened humanity's horizons, this expanded perception has the potential to influence not only science, but also art, philosophy, and all aspects of human creativity, inviting us to rethink the cosmos and our place in it. Beneath the surface of our everyday lives, governed by the familiar pull of gravity and the invisible bonds of electromagnetism, lies a hint of something more, something that challenges the established order of forces that shape our reality. For centuries, the human intellect has tried to make sense of the majestic diversity of nature, unraveling thread by thread the laws that govern all things visible and invisible. And yet, as we look ever deeper into the heart of matter and the vast expanse of space, we are increasingly confronted with anomalies, behaviors that defy explanation, phenomena that slip through the cracks of our most trusted theories. This is where the rumor of a fifth force, a force beyond gravity, electromagnetism, and nuclear interactions, originates. So today we decided to ask, how possible is the existence of this fifth architect of the universe, forming the very essence of matter and energy? First, let's start with the basics to make sure we're all on the same page. 4 fundamental forces are at work in the vastness of the universe, each playing its unique role, shaping everything from the microcosm of subatomic particles to the macrocosm of galaxies. Gravity, often considered the force most familiar to us, dictates the motion of planets and stars, causing celestial bodies to move in their orbits. It's the same force that keeps our feet on Earth and makes apples fall from the tree. Next, we'll look at electromagnetism. This force is responsible for the glow of auroras, the brilliance of stars, and the very light traveling through the vastness of space to meet our eyes. Electromagnetism controls the interaction of charged particles, creating everything from palpable warmth of sunlight to the invisible waves that carry our voices through the air. Another force at the heart of every atom is the strong nuclear force. It reigns supreme within the atomic nucleus, ensuring protons and neutrons remain locked in a strong bond. This force is the reason for the existence of the glowing crucible of the Sun and the grandest explosions in the universe supernovae. Although limited in range, it is the key to the immense power of stars, driving thermonuclear reactions. Finally, we encounter the weak nuclear force, a subtle shaper of the elements. The weak nuclear force plays a crucial role in the nuclear processes that power stars and lead to the synthesis of various elements. This force is necessary for the sun to shine and for the very existence of elements beyond hydrogen in the periodic table. These four forces describe the complex interaction of matter and energy that dictates the universe's structure, behavior, and evolution. Understanding them is essential to understanding the fundamental principles governing our world. In the realm of infinitesimals, where atoms are their universes, four fundamental forces manifest their influence uniquely. The strong and weak nuclear forces acting within the atomic nucleus are central to this scale. The strong nuclear force, with its iron grip, ensures the stability of the atomic nucleus. This force is so powerful that it overcomes the repulsion between positively charged protons, binding them with neutrons to form the nucleus, the heart of every atom. Though powerful, this force is remarkably short-ranged. Its influence barely extends beyond the nucleus. Meanwhile, the weak nuclear force makes itself known through beta decay, transforming a neutron into a proton, while emitting an electron and an antineutrino. Although weaker and short-lived than the strong nuclear force, this force plays a key role in the alchemical transformations within stars, helping to synthesize the elements that make up our world. Translating our view of the celestial interaction of planets and stars, gravity and electromagnetism begin to dominate the scene. Overarching gravity governs the orbits of planets around stars, holds moons bound to planets, and gives structure to galaxies. Electromagnetism, on the other hand, is the architect of light. From the violent flares of the sun to the serene glow of distant stars, this force generates the entire electromagnetic spectrum, from radio waves to gamma rays, providing the visibility of the cosmos and the fundamental interactions between charged particles in its vastness. On the larger scales of galactic superclusters, gravity is the undisputed ruler. It weaves together the fabric of the cosmos and dictates the motion of galaxies and the structure of the universe itself. However, things have become much more complicated than we previously thought. Scientists continue to encounter phenomena that defy our established quartet of forces. These anomalies suggest the existence of a force beyond gravity, electromagnetism, and nuclear interactions. One such mystery arose in the bowels of particle physics. In the late 20th century, experiments designed to investigate the characteristics of fundamental particles began to reveal inconsistencies. Measurements of the decay rates of some particles and the gravitational behavior of objects on microscopic scales hinted at effects not accounted for by the standard model of particle physics. Even pioneers such as Ettore Majorana and Julian Schwinger suggested the existence of additional forces, and their theories offered the first mathematical framework to account for these anomalies. Schwinger, in particular, proposed a fifth force with a small radius of action that could subtly influence the interaction of particles and yet be undetectable in broader gravitational measurements. Subsequent studies highlighted several anomalies that current theories of physics cannot fully explain. A reanalysis of the Ethos experiment by Professor Fishback and his colleagues back in 1986 revealed inconsistencies in gravitational acceleration that depended on the composition of materials, indicating non-Newtonian coupling. Similarly, in the 1996 revisit by Fishback and Talmage, the motivation for studying the fifth force was the recognition that some experimental results could not be explained by known forces, including gravitational anomalies and deviations in kaon regeneration experiments that hinted at an anomalous energy dependence that could arise from an external field. The initial speculation around the fifth force was driven mainly by a desire to explain these anomalies. The hypothesis suggested the existence of a new medium-range force, similar to gravity, arising from the exchange of a new ultralight boson. This boson was based on numerous Planck scale theories predicting such bosonic fields, altering the usual gravitational interaction between masses. Subsequent studies aimed to find new theories and hypotheses to explain the observed anomalies and further test the fifth force hypothesis. They consider the influence of a massive hypercharge field, proposing the exchange of hyperphotons to create a potential that could explain the anomalies observed in the Ethos experiment. Despite the lack of conclusive evidence for such a force, continuing anomalies in the experimental data and the predictions of various unifying theories leave the search for a fifth force an open question. The search for a fifth power has gained new momentum in recent years. The Atomki experiment, led by scientists from the Hungarian Academy of Sciences, has revealed one of the most tantalizing hints. Observing an unexpected anomaly in the decay of beryllium-8 atoms suggested the influence of a force not predicted by existing theories, a potential carrier particle called the X17 boson. This discovery has sparked a flurry of theoretical work, with physicists worldwide proposing new models to explain the Atomki anomaly and similar observations. Theories involving dark photons, photophobic forces, and hidden sectors of the universe have emerged, each trying to weave these anomalies into a coherent narrative. Around the world, advanced research centers have become springboards for this monumental quest. From the vast CERN complex, home to the colossal Large Hadron Collider, to the intricate underground labyrinths that house the ultra-sensitive detectors of the Lux-Zeppelin dark matter experiment. These are modern temples of science. Here, amid the hum of superconducting magnets and the soft glow of computer screens, physicists push the boundaries of the known universe. At the heart of the LHC, amid a maze of tunnels and the hum of accelerating particles, scientists explore the fabric of reality. Here, particles accelerate to near-light speeds and then collide, giving birth to a fleeting microcosm where the laws of physics can be observed in their most primal form. In these high-energy collisions, signs of the fifth force, unveiled in the consequences of subatomic interactions, may lurk. One experiment that shook up conventional wisdom was the observation of anomalous decay of B mesons in the LHCb experiment. These mesons, consisting of a lower quark bound to a lighter quark, exhibited a decay pattern that deviated from the predictions of the standard model. Decay into electrons and muons, particles that should be treated equally by the known forces, showed an unexpected bias. This discrepancy hinted at an unseen influence, perhaps the bearer of a new force, subtly altering the behavior of fundamental particles. On the other side of the Atlantic, Fermilab has embarked on a search using the Muon G-2 experiment. Similar to heavy electrons, muons have a magnetic moment, a property that dictates how they interact with magnetic fields. The standard model of particle physics, a theory that's withstood the scrutiny of countless experiments, predicts this magnetic moment with surprising accuracy. However, the Muon G-2 experiments measured a value that stubbornly disagrees with these predictions. This deviation suggests that muons may be feeling the attraction of an unknown force whose influence eludes our current understanding. The centerpiece of this experiment is the muon, an elementary particle similar to an electron, but with about 200 times the mass. These particles constantly bombard the Earth as a byproduct of cosmic rays striking the atmosphere, making them both ubiquitous and valuable for scientific research. The Muon G2 experiment is based on the desire to accurately measure the anomalous magnetic dipole moment of the muon, often referred to as the G2 value. This physical quantity reflects the oscillation or precession of the muon under the influence of a magnetic field. the Standard Model of Particle Physics, the most reliable framework for understanding the fundamental forces and particles of the universe, offers accurate predictions for this quantity. However, if experimental measurements deviate from these predictions, this may indicate the influence of forces or particles beyond our current theoretical picture.
The magnet used for the Muon G-2 experiment is a superconducting magnet. It has a 50-foot diameter. We run more than 5,000 amps through it, which produces a field of approximately 1.45 Tesla, which is about 30,000 times the magnetic field of the Earth. So it's a very strong magnet.
Inside this magnet, muons are trapped and observed as they cross the magnetic field. However, despite all their power, muons embody the ephemeral nature of the subatomic world. They live only 2.2 microseconds before decaying into electrons and neutrinos. This short lifespan of 2 millionths of a second is a blink of cosmic time. But it is just long enough for physicists to make measurements. By meticulously measuring the precession rate of muons, scientists can compare experimental results with theoretical predictions derived from the Standard Model. The first results of Fermilab's Muon G2 experiment, published in April 2021, have aroused the scientific community's interest. The measured precession rate of muons showed a significant discrepancy with the predictions of the Standard Model. In particular, the muons oscillated at a higher rate than expected, suggesting the possible influence of unknown particles or forces interacting with the muons. This discrepancy, expressed as a deviation with a statistical significance of 1 in 40,000, means there is a 99.9975% chance that this result is not a simple statistical fluke, but a tangible sign of new physics. The implications of the results of the Muon G2 experiment extend far into the realm of cosmology and particle physics. If the observed discrepancy is confirmed, it could provide insight into the pervasive mysteries of dark matter, dark energy, and the imbalance between matter and antimatter. In a nutshell, dark matter, which makes up approximately 85% of the matter in the universe, remains undetected in direct experiments, and is known only through its gravitational effects on cosmic structures. Similarly, dark energy, which drives the universe's accelerated expansion, accounts for only 74% of its energy content, and its nature is largely unknown. The asymmetry of matter and antimatter, in turn, raises the question of why the universe is dominated by matter. Despite theoretical predictions of equal amounts of matter and antimatter at the origin of the universe, the results of the Muon G2 experiment may hint at new particles or interactions affecting the behavior of the muon, which may be related to the elusive dark matter or other unknown aspects of the universe. In addition, these results may help study antimatter and the asymmetry between matter and antimatter, shedding light on the conditions that led to the predominance of matter in the universe. In the context of the past successes of the Standard Model, the G2 Muon experiment represents a turning point in the ongoing quest to understand the universe's fundamental structure. The Standard Model has had a profound impact on modern physics, providing significant technological advances and deepening our understanding of the structure of the universe. Can such experiments illuminate the mysteries of dark matter, dark energy, and the asymmetry of matter and antimatter? The G2 Muon experiment could herald a new chapter in our understanding, guiding us toward a more complete theory of the universe. We look forward to further research and confirmation of experiments by scientists in this fundamental area of physics.